In the vast darkness of space, orbits one small world that we call home. But beyond our sun lie trillions of stars, and orbiting those stars are worlds beyond imagination. Some scorching hot, some frozen solid, and even some that might harbor life. Welcome to Stellar Worlds, where we explore some of the most fascinating planets in the universe. Are you ready? Let's begin. For our first planet today, let's uncover the evaporating world of GJ9827b and the Radius Valley Mystery. 97 light-years from Earth, in the constellation Pisces, orbits a planetary system that has become one of the most intensively studied in the galaxy. GJ9827, a moderately bright red dwarf star hosting 3 planets, all super-Earths ranging from 1.6 to 2.0 times Earth's radius, all orbiting closer than Mercury orbits our Sun. GJ9827b, the innermost world, completes an orbit every 1.2 days, just 29 hours. It receives intense stellar radiation, heating its surface to over 1,200 Kelvin. At 1.64 Earth radii, it sits precisely at the Radius Valley, the boundary separating rocky super-Earths from volatile-rich mini-Neptunes. This critical position makes it invaluable for understanding how planets lose their atmospheres and evolve from one type to another. Recent observations with the James Webb Space Telescope have revealed something remarkable. GJ9827b appears to be actively losing its atmosphere to space, with water vapor detected in the escaping gas. This planet is caught in the act of transformation, possibly evolving from a water-rich mini-Neptune to a rocky super-Earth over millions of years. What we're witnessing is planetary evolution in real time. By 2017, the K2 mission had been operating for 4 years, discovering hundreds of planets by observing different fields every 80 days. Campaign 12 focused on a region in Pisces, targeting stars suitable for detailed follow-up studies. GJ9827, also cataloged as K2-135 and HD 205739, was a priority target, a magnitude 10.4 K dwarf just 97 light-years away, bright and nearby enough for extensive characterization. During the 80-day campaign, K2 detected periodic transit signals at 3 different periods: 1.2 days, 3.6 days, and 6.2 days. 3 planets, all transiting from our perspective, a jackpot for comparative planetology. The transit depths revealed planetary sizes. The innermost planet, GJ9827b, at 1.64 Earth radii, the middle planet C at 1.29 Earth radii, and the outermost D at 2.01 Earth radii. All 3 fell in the critical size range between Earth and Neptune, the regime where planets transition from rocky to volatile-rich compositions. GJ9827's proximity and brightness made it ideal for rapid characterization. Within months of the K2 announcement, multiple teams had measured the planet's masses and begun atmospheric studies. We used precision radial velocity instruments, HARPs, PFS, HIRES, to measure the star's wobble induced by the planet's gravity. For GJ9827b, the innermost planet, we detected a radial velocity semi-amplitude of about 3 meters per second. This translates to a mass of approximately 3.7 Earth masses. Combined with the 1.64 Earth radius, we calculated a density of about 4.9 g/cm superscript 3, less dense than Earth's 5.5 g/cm superscript 3, but denser than pure rock, suggesting either a water-rich composition or rocky with a thin atmosphere. The discovery was announced in 2017, with detailed characterization papers following in 2018. The 3-planet system immediately became a high-priority target for atmospheric studies, comparative planetology, and understanding the Radius Valley. GJ9827 is a K-type dwarf star, cooler than the Sun but hotter than red dwarfs, creating a moderate radiation environment for its planets. GJ9827 is an excellent host for planet studies. At magnitude 10.4, it's among the brightest stars hosting small planets accessible to transmission spectroscopy. The star's maturity and relatively low activity are important. Younger, more active stars produce flares and radiation that complicate atmospheric observations and affect planetary evolution. GJ9827's age means its planets have had billions of years to evolve to their current states. The GJ9827 system is compact, with all three planets orbiting closer to their star than Mercury orbits the Sun. The GJ9827 system is like a laboratory for studying the radius valley. We have three planets in the same system, all receiving different stellar fluxes, all with different sizes straddling the valley. GJ9827c appears to be a dense, rocky super-Earth that lost or never had a substantial atmosphere. GJ9827d appears to be a volatile, rich mini-Neptune with lower density. And GJ9827b sits right at the boundary, the most interesting planet for understanding the transition. GJ9827b's radius of 1.64 Earth radii places it precisely at one of the most important boundaries in planetary science, the radius valley, also called the Fulton Gap. The radius valley is a dearth of planets between about 1.5 and 2.0 Earth radii. Below this gap, planets are predominantly rocky super-Earths that lost or never had substantial hydrogen-helium envelopes. Above it, they're mini-Neptunes with thick volatile envelopes, water, hydrogen, or both. The valley exists because of photoevaporation. Stellar high-energy radiation strips atmospheres from small planets, creating two distinct populations. Planets at the valley edge, like GJ9827b, are caught in transition, possibly in the process of losing their atmospheres right now. At 1.64 Earth radii, GJ9827b could be either a rocky super-Earth with a thin remaining atmosphere or a water-rich world with a steam atmosphere. Its density of 4.9 g/cm superscript 3 is intermediate, higher than a pure water world would be, but lower than pure rock, leaving the composition ambiguous. Orbiting at just 0.019 AU with a period of 1.2 days, GJ9827b experiences extreme conditions. At these temperatures, GJ9827b's surface will be molten if rocky, or covered in a thick steam atmosphere if water-rich. Any hydrogen-helium atmosphere would be rapidly escaping to space under the intense stellar radiation. The planet is caught in a hostile environment that actively strips away its atmosphere over millions of years. With a radius of 1.64 Earth radii and mass of 3.7 Earth masses, GJ9827b's internal composition remains uncertain. Three scenarios are plausible. Scenario 1. Rocky super-Earth with thin atmosphere. Iron silicate core and mantle similar to Earth. Currently losing atmosphere to photoevaporation. Will eventually become bare rocky core. Scenario 2. Water world. Rocky core with 20 to 40% water by mass. Thick steam atmosphere for vaporized ocean. Water beneath steam layer might be supercritical fluid. Scenario 3. Evaporating mini-Neptune. Small rocky core with originally thick H/He envelope. Transitioning toward rocky super-Earth composition. The observed density of 4.9 g/cm superscript 3 slightly favors scenarios 1 and 3. Either a rocky planet with a small remaining atmosphere, or a planet that had a larger envelope and is losing it. Scenario 2, a pure water world, would typically have lower density unless the water is extremely compressed. But all three remain possible. This is where atmospheric observations become crucial. Detecting what's in the atmosphere tells us what the planet is made of. In 2022 and 2023, the James Webb Space Telescope observed GJ 9827b multiple times, searching for atmospheric signatures. The results, published in 2024, were both expected and surprising. We observed GJ 9827b with JWST's NIR spec and NIRIS instruments, covering wavelengths from 0.8 to 5 microns. Given the planet's size, mass, and position at the radius valley, we had three possible outcomes. 1. Detect a thick hydrogen-rich atmosphere with strong molecular features. 2. Detect a thinner steam atmosphere dominated by water vapor. Or 3. Detect nothing, a flat spectrum indicating no substantial atmosphere. What we found was primarily option 2, with some surprises. The JWST observations detected water vapor in GJ 9827b's atmosphere, but not the thick, stable steam atmosphere of a water world. Instead, the water appears to be part of an actively evaporating atmosphere. Key JWST findings, 2024. Water vapor, H2O, detected. Clear absorption features at 1.4, 1.9, and 2.7 microns indicating water vapor presence. Abundance appears substantial, but precise measurement complicated by atmospheric structure. No hydrogen and helium signature. Absence of expected features from hydrogen-rich atmosphere suggests either 1. The planet has lost most primordial H/E envelope, or 2. Atmosphere is dominated by heavier molecules like water. Evidence for atmospheric escape. Spectral features consistent with extended, escaping atmosphere rather than stable bound atmosphere. Water vapor might be escaping along with the overall atmospheric loss. Possible metal enrichment. Some analyses suggest the atmosphere might be enriched in heavy elements compared to solar composition, indicating either water world origin or remnant of evaporated H/E envelope. The water vapor detection is exciting but raises questions. Is this a water world with a thick steam atmosphere? Or is it a planet that had a hydrogen-helium envelope, which is now evaporating, and we're seeing water that was always present beneath the H/E layer now becoming exposed? The spectral features suggest active atmospheric loss. This isn't a stable atmosphere, but one being stripped away by stellar radiation. The favored interpretation is that GJ 9827b is actively losing its atmosphere through photoevaporation, and the detected water vapor is part of the escaping gas. The evaporation model. Stage 1, distant past. GJ 9827b had a thicker atmosphere, possibly hydrogen-helium with water vapor or pure steam atmosphere if it formed as water world. Stage 2, recent past to present. Intense stellar UV and X-ray radiation heats the upper atmosphere, giving atoms and molecules enough energy to escape gravity. Hydrogen and helium escape preferentially due to low mass. Stage 3, current observations. Hydrogen largely depleted. Water vapor now comprises significant fraction of remaining atmosphere. Water molecules also escaping, but more slowly than hydrogen. Stage 4, future. Continued evaporation will strip remaining atmosphere over millions of years. Planet will transition to bare rocky core or water-depleted rocky planet. We're witnessing GJ 9827b in the middle of this transformation, caught in the act of losing its atmosphere and evolving from one type of planet, volatile-rich, toward another, rocky. This is planetary evolution happening on timescales we can observe and study. The three GJ 9827 planets tell a coherent story about how stellar irradiation determines planetary composition and evolution. The GJ 9827 system beautifully demonstrates the radius valley in action. The innermost planet receives so much radiation it lost its atmosphere entirely. The outermost receives little enough that it retained a thick envelope. And GJ9827b is caught in between, receiving just enough radiation to drive atmospheric escape, but not so much that it's already finished. We're seeing the valley formation process happening right now. For decades, theoretical models predicted that stellar high-energy radiation should strip atmospheres from small close-in planets, creating the observed radius valley. GJ9827b provides direct observational evidence. Based on the atmospheric observations and stellar radiation environment, scientists can estimate GJ9827b's mass loss rate. This rapid mass loss means GJ9827b is changing on astronomically short timescales. In just 10 million years, a blink in cosmic time, its appearance and properties could be dramatically different. We're witnessing active planetary evolution. GJ9827b joins a small but growing number of planets where atmospheric escape has been directly detected or strongly inferred. GJ9827b is unique in being at the radius valley boundary with detected water vapor escape. It's providing unprecedented insight into how planets transition from one compositional class to another. The initial JWST observations raised as many questions as they answered. Future observations aimed to resolve the remaining mysteries. None of the GJ9827 planets orbit in the traditional habitable zone, but the outermost planet GJ9827d has intriguing properties. 97 light-years from Earth, GJ9827b continues its rapid orbit. Every 29 hours, just over a day, it completes another circuit around its orange dwarf star. The same hemisphere always faces the star, baked to 1,200 Kelvin. The other knows perpetual night, only slightly cooler. We're witnessing something profound, planetary evolution in action. Every second, hundreds of millions of kilograms of water vapor escape from GJ9827b's atmosphere, driven away by intense stellar radiation. The planet is transforming, caught between past and future. No longer the volatile, rich world it once was, not yet the bare, rocky core it will become. In the planet's sky, if there were anyone to see it, the star would hang motionless, enormous and blazing. The thin atmosphere would be in constant motion, heated gas rising and escaping to space. The horizon would shimmer with heat, and above, a thin veil of escaping gas would create an ethereal glow, the planet's atmosphere leaving forever. 10 million years from now, GJ9827b will be different. Perhaps its atmosphere will be completely gone, leaving a bare, rocky surface. Perhaps only a thin remnant will remain. The planet is ephemeral, not in the sense that it will cease to exist, but that it will cease to be what it is now. GJ9827b has taught us that the radius valley, the gap in the planet-size distribution, is not just a statistical feature, but a dynamic process. Planets don't simply exist on one side or the other. They can transition from above the valley to below it through atmospheric loss. It has provided observational confirmation of photoevaporation theory, showing that stellar radiation really does strip atmospheres and create the division between rocky super-Earths and volatile-rich mini-Neptunes. The water vapor detected in its escaping atmosphere is direct evidence of this process in action. The GJ9827 system reminds us that planetary systems are not static. They evolve. Planets change over billions of years, shaped by their star's radiation, their own internal heat, and the initial conditions of their formation. Understanding these evolutionary processes is key to understanding the diversity of planets we observe throughout the galaxy. This is GJ K2-9827b. The evaporating world. A super-Earth at the Radius Valley boundary, caught in the act of losing its atmosphere to space. A planet where water vapor streams away under intense stellar radiation, transforming it from volatile-rich to rocky over millions of years. A reminder that planets are not permanent in their properties, that atmospheres are fragile, and that understanding planetary evolution requires observing planets caught in transition. Worlds like GJ9827b that are changing before our eyes. Scientists continue to learn more about this strange planet. The atmosphere continues to escape, and through this evaporating world, we witness planetary evolution as it happens, revealing the dynamic processes that shape planets throughout the universe. If you're a heavy metal fan, you're going to love the iron heart of K2-229b and the mystery of exposed planetary cores. 339 light-years from Earth, in the constellation Virgo, orbits one of the most extraordinary planets ever discovered. K2-229b, a world smaller than Earth yet denser than any planet in our solar system, with a composition suggesting it's not a normal rocky planet, but an exposed planetary core. With a density estimated at 9 to 11 grams per cubic centimeter, far exceeding Earth's 5.5 g/cm superscript 3, K2-229b is approximately 70 to 80% iron by mass. For comparison, Earth is only 32% iron, and Mercury, the densest planet in our solar system, is about 65% iron. K2-229b is more metal than rock, possibly the exposed iron core of what was once a much larger planet. Orbiting at just 0.012 EU, 3 times closer than Mercury orbits our Sun. With a period of only 14 hours, K2-229b experiences surface temperatures exceeding 2,000 Kelvin, hot enough to vaporize rock. How did this planet form? Was it always an iron-rich world, or did catastrophic collisions or intense stellar radiation strip away its rocky mantle, leaving only the dense metal core? K2-229b represents a new category of exoplanets, supermercuries, ultra-dense rocky worlds that challenge our understanding of planet formation and evolution. Its extreme properties make it a natural laboratory for studying planetary interiors, collision dynamics, and the most extreme environments planets can endure. By 2016, the K2 mission had been operating for 3 years, discovering hundreds of planets by observing different fields every 80 days. Campaign 10 targeted a region rich in bright stars suitable for detailed follow-up studies. K2-229, cataloged as EPIC 2-119-16756, was a magnitude 11.0 K-dwarf star approximately 339 light-years away. During the 80-day campaign, K2 detected periodic transit signals every 14.3 hours with a depth of about 0.03%, indicating a small planet, roughly Earth-sized or slightly smaller. The extremely short period immediately flagged it as an ultra-short period, USP, planet, a rare class orbiting closer than 0.02 AU with periods less than 1 day. Ultra-short period planets are rare. Only about 0.5% of stars host them. They're scientifically valuable because their extreme proximity to their stars subjects them to intense radiation, tidal forces, and possibly catastrophic processes that can reveal planetary interiors. Determining K2-229b's true nature required measuring its mass through radial velocity observations, detecting the tiny wobble the planet induces in its star's motion. We used the HARP spectrograph at La Silla Observatory and other instruments to conduct intensive radial velocity monitoring. For such a small planet, the radial velocity amplitude is tiny. We measured about 2.3 meters per second, right at our detection limit. This required dozens of high-precision observations and careful analysis to separate the planetary signal from stellar noise. The result was shocking. A mass of approximately 2.6 Earth masses combined with a radius of 0.76 Earth radii gave a density of approximately 10 grams per cubic centimeter. K2-229b's density exceeded pure iron under normal conditions, suggesting it's composed of iron compressed by immense pressure or iron mixed with even denser elements. The discovery was announced in 2018, immediately recognized as one of the densest small planets known, a potential exposed planetary core. K2-229 is a K-type dwarf star, cooler and smaller than the Sun, but more massive and luminous than red dwarfs. K2-229's supersolar metallicity, 20% more heavy elements than the Sun, is significant. Metallicity correlates with planet formation efficiency and composition. The enrichment in iron and other metals might be related to K2-229b's unusual iron-rich composition. Whether the star's high metallicity contributed to forming an iron-rich planet, or whether the star accreted iron-rich material from planetary collisions that created K2-229b, is an open question. K2-229b is not alone. K2 observations revealed 2 additional transiting planets in the system, making it a compact, multi-planet system. The K2-229 system is fascinating because the innermost planet is ultra-dense and iron-rich, while the outer planets are volatile-rich with low densities. This compositional gradient, dense inner planet, puffy outer planets, might tell us about formation conditions, migration history, or catastrophic events that affected only the inner planet. Understanding why K2-229b is so different from its siblings is key to understanding its origin. K2-229b is classified as a supermercury, a rocky planet with anomalously high iron content and density, reminiscent of Mercury, but even more extreme. K2-229b's internal structure is extraordinary. With 70 to 80% iron by mass, the iron core must comprise more than half the planet's radius, possibly 60 to 70%. The remaining rocky mantle is thin, perhaps only a few hundred kilometers thick. This is fundamentally different from Earth, where the iron core is 55% of the radius, but only 32% of the mass. K2-229b is essentially a giant iron ball with a thin rocky coating. Mercury, with about 65% iron by mass, is the densest planet in our solar system and has long been anomalous. K2-229b takes Mercury's unusual composition to an extreme. The supermercury classification raises fundamental questions. How do such iron-rich planets form? Are they the natural outcome of certain formation conditions, or are they the remnants of catastrophic processes that stripped away their rocky mantles? 3 main hypotheses have been proposed to explain K2-229b's extraordinary iron content. Scenario 1. Giant impact hypothesis. Similar to the theory for Mercury's formation, K2-229b might have experienced one or more giant collisions early in its history that preferentially removed the rocky mantle, while leaving the denser iron core largely intact. Scenario 2. Photoevaporation of rocky mantle. Intense stellar radiation during the star's active young phase vaporized and blew away the planet's rocky mantle through photoevaporation, leaving the iron core, which is harder to vaporize due to iron's higher boiling point. Scenario 3. Primordial iron enrichment. K2-229b formed in an unusually iron-rich region of the protoplanetary disk, perhaps due to temperature-dependent condensation of iron close to the star or enrichment from earlier stellar processes. Each scenario has strengths and weaknesses. My suspicion is that K2-229b's extreme composition required multiple processes. Perhaps it formed somewhat iron-enriched, then experienced a mantle-stripping collision, and finally underwent some photoevaporation at its current ultra-short period orbit. Disentangling these processes requires comparing many supermercuries and understanding what conditions produce different outcomes. Orbiting at just 1.8 million kilometers, about 5 times the Earth-Moon distance, K2-229b experiences conditions more extreme than any planet in our solar system. On K2-229b's day side, temperatures exceed iron's melting point. The surface might be a thin crust of solid iron oxides and silicates floating on an ocean of molten metal and rock. The star dominates the sky, appearing enormous. About 30 times larger than the Sun appears from Earth, bathing the landscape in blazing light and heat. The night side, though cooler, remains far hotter than any place in our solar system. Around 1,500 to 1,800 K, glowing dull red from retained heat despite never seeing the star. A key question about K2-229b is whether it retains any atmosphere at all. At 2,200 K, with intense stellar radiation, any primordial hydrogen-helium atmosphere would have escaped long ago. But could a secondary atmosphere exist? We've attempted transmission spectroscopy observations of K2-229b using space-based and ground-based telescopes. The planet's small size makes atmospheric signals weak. So far, observations are consistent with either no atmosphere or a very minimal one. Perhaps a thin layer of vaporized rock from the molten surface creating a temporary mineral atmosphere that rains back down on the night side. At 2,200 K, K2-229b's surface temperature exceeds the boiling points of many minerals. This could create an exotic mineral atmosphere. A mineral atmosphere would be transient and dynamic. Rock vaporizes on the hot day side. The vapor forms a temporary atmosphere that circulates toward the night side where it cools and condenses, raining back as molten rock or solid minerals. This cycle, evaporation, atmospheric transport, condensation, precipitation, is like Earth's water cycle but with vaporized rock instead of water. It's an alien hydrological cycle operating at extreme temperatures. While transmission spectroscopy searches for atmospheric absorption, eclipse observations measure the planet's thermal emission, the heat it radiates to space. Spitzer eclipse observations attempted. The planet's small size and relatively faint host star made eclipse observations challenging. Attempts with Spitzer suggested a hot day side consistent with 200 K, but with large uncertainties. Understanding K2-229b's interior requires sophisticated models accounting for how iron and rock behave under extreme pressure and temperature. K2-229b's internal pressure reaches 800 GPa at the center, about 8 million times Earth's atmospheric pressure. At these pressures, iron's properties change. It becomes denser, conducts heat differently, possibly exhibits exotic crystal structures. The planet's interior is effectively a laboratory for studying iron at extreme conditions impossible to replicate on Earth. On Earth, our magnetic field is generated by convection in the liquid iron outer core. Given K2-229b's enormous molten iron core, could it generate an even stronger magnetic field? In principle, K2-229b's vast molten iron core, possibly half the planet's radius or more, should be capable of generating a magnetic field through dynamo action. The rapid rotation from tidal locking provides the necessary rotation for the Coriolis effect. However, The intense stellar wind at such a close orbit might compress or strip away any magnetic field. Detecting a magnetic field on K2-229b would be extraordinary. It would tell us about the planet's interior dynamics and how magnetic fields operate in extreme environments. K2-229b is among the densest small planets known, but it's not unique. A handful of other supermercuries have been discovered, allowing comparative studies. These supermercuries cluster in ultra-short orbits, periods less than 1 day, or in systems with unusual architectures. The pattern suggests that extreme processes, whether impacts, evaporation, or formation in unusual conditions, are required to produce such iron-rich worlds. Supermercuries are rare. Only a few have been definitively identified among thousands of known exoplanets. But patterns are emerging. We estimate that less than 1% of rocky planets are supermercuries. They're preferentially found in ultra-short orbits and in metal-rich stellar systems. The rarity suggests that producing such iron-rich planets requires special circumstances, whether giant impacts at just the right angle and velocity, extreme stellar irradiation during the early high-activity phase, or formation in unusually iron-rich disk regions. Each supermercury we discover helps constrain which formation pathways are most likely. Studying supermercuries like K2-229b reveals the diversity of rocky planet formation and the extreme processes that shape planetary composition. Key lessons. 1. Giant impacts are common. The existence of supermercuries supports models predicting frequent giant collisions during late-stage planet formation. Our moon formed from such an impact on Earth. 2. Compositional diversity is vast. Rocky planets range from iron-poor, Mars, 25% iron, to iron-rich, K2-229b, 75% iron. Formation location, collision history, and stellar environment all affect final composition. 3. Extreme environments shape evolution. Ultra-short orbital periods subject planets to intense radiation and tidal forces that can fundamentally alter their structure and composition. 4. Mercury isn't unique. Our solar system's Mercury is not an anomaly, but part of a broader population of iron-enriched planets produced by violent planetary formation processes. Despite its small size, K2-229b remains an attractive target for JWST atmospheric studies because of its extreme properties and nearby, relatively bright host star. The next generation of ground-based telescopes, extremely large telescopes with 30 to 40-meter mirrors, could detect individual spectral lines from vaporized minerals. K2-229b is experiencing ongoing evolution, atmospheric escape, surface melting, possible volcanism. Long-term monitoring could reveal changes. 339 light-years from Earth, K2-229b continues its rapid orbit. Every 14 hours, every half-day, it completes another circuit around its orange dwarf star. The same hemisphere always faces the star, baked to temperatures exceeding 2,200 Kelvin. Imagine approaching this world. From space, it appears small, only 3/4 Earth size. But its mass surprises, more than 2.5 Earth masses compressed into this small volume, creating gravity 4.5 times Earth's pull. Descending toward the day side, the heat becomes overwhelming. The star dominates the sky. 30 times larger than the Sun appears from Earth. The surface glows orange-red, not from reflected starlight, but from its own thermal emission, molten rock radiating heat like hot coals. Landing is impossible. The surface is partially or fully molten, a lava ocean of liquid silicates floating on an even deeper ocean of molten iron. The thin rocky crust that might exist in cooler regions fractures and reforms constantly, iron-rich rock flowing and solidifying in an endless cycle. Above, a faint haze, not water vapor or atmospheric gases, but vaporized rock. Sodium and potassium atoms drift in the heat. Iron vapor rises from the hottest regions. Silicon monoxide molecules form and break apart. This is the mineral atmosphere, transient, alien, created and destroyed moment by moment. Thousands of kilometers below, beneath the molten silicates and iron, lies the heart of the planet, a solid iron core compressed to extreme density by the immense pressure. This is what remains of a world that might once have been much larger. Or, this is a planet that formed under extraordinary conditions we barely understand. K2-229b has taught us that rocky planets can be far more diverse than our solar system suggests. That iron-rich worlds exist where the core dominates the planet's structure. That some planets are more metal than rock, challenging our categories and definitions. It has revealed that planetary formation is violent and chaotic. That giant collisions can strip away a planet's rocky mantle, leaving the iron core exposed. Or that stellar radiation can vaporize rock over millions of years. Or that some regions of protoplanetary disks are so rich in iron that ultra-dense planets form naturally. K2-229b reminds us that planets are not just scaled versions of Earth. They're individual worlds shaped by their formation histories, their stars, their collisions, their orbital evolution. Each planet tells a story, and K2-229b's story is one of iron, extreme heat, and perhaps catastrophic origins. This is K2-229b, the Iron Heart, an ultra-dense supermercury with 70 to 80% iron by mass, orbiting every 14 hours in a molten hell hot enough to vaporize rock. A planet that is possibly an exposed planetary core, revealing its metal interior to the universe. A reminder that the diversity of planets exceeds our solar system's examples. That rocky planets range from iron-poor to iron-rich, from cool to molten, from Earth-like to utterly alien. And that by studying extremes like K2-229b, we understand the full range of planetary possibilities throughout the cosmos. The observations continue. The planet orbits on, and through this iron heart, we see into the violent history and extreme diversity of rocky worlds throughout the galaxy. If you think inflation has gotten out of hand, you might not be ready for the swollen giant, WASP-112b, and the physics of extreme inflation. 467 light-years from Earth, in the constellation Hercules, orbits a gas giant that challenges our understanding of planetary physics. WASP-112b, a planet with nearly Jupiter's mass but swollen to 1.88 times Jupiter's radius, giving it a density of only 0.16 grams per cubic centimeter. Less dense than cork, less dense than styrofoam, among the puffiest hot Jupiters ever discovered. The cause of this extraordinary inflation, one of the most intense stellar radiation environments known. WASP-112b orbits just 0.0294 AU from its bright F-type star, closer than any planet in our solar system, receiving approximately 2,400 times the stellar flux Jupiter receives from the Sun. The radiation is so intense that it heats the planet's atmosphere to over 1,800 K and deposits energy deep into the interior, preventing the planet from contracting under its own gravity. WASP-112b has become a crucial test case for understanding hot Jupiter inflation, one of the most puzzling phenomena in exoplanet science. Why are some hot Jupiters compact and dense while others are bloated and puffy? What mechanisms transport stellar energy into planetary interiors? And what are the limits of how large a gas giant can become before atmospheric escape begins stripping away its envelope? This is the story of a swollen giant, a planet pushed to its limits by stellar radiation, revealing the physics of atmospheric heating and planetary inflation in extreme environments. The Wide-Angle Search for Planets, WASP, have been discovering hot Jupiters since 2006, using small automated telescopes to detect the periodic dimming when planets transit in front of their stars. By 2012, WASP South had accumulated thousands of observations of millions of stars. WASP 112 was cataloged as GSE 0548800788, a magnitude 11.4 F-type star in Hercules. Between 2004 and 2011, Super WASP South accumulated extensive observations. Our automated pipeline detected periodic transit signals every 3.43 days with a depth of approximately 1.6%, indicating a large planet, significantly bigger than Jupiter, orbiting very close to the star. The large transit depth, despite the bright F-type star, immediately suggested an inflated hot Jupiter. The transit signature was clear and consistent across multiple observing seasons. WASP 112b was flagged for follow-up observations to confirm its planetary nature and measure its mass. Confirming WASP 112b required radial velocity measurements to rule out false positives and determine the planet's mass. We used Corelli at La Silla Observatory and other spectrographs to measure WASP 112's radial velocity over multiple orbits. The measurements revealed a wobble with a semi-amplitude of about 150 meters per second, consistent with a massive planet in a close orbit. We determined a mass of approximately 0.88 Jupiter masses. Combined with the large radius from transit observations, this gave a surprisingly low density, about 0.16 g/cm superscript 3, making WASP 112b one of the puffiest hot Jupiters known. The discovery was announced in 2014, immediately recognized as an excellent case study for extreme hot Jupiter inflation. With such low density and intense stellar irradiation, WASP 112b offer a natural laboratory for testing inflation mechanisms. WASP 112 is an F-type star, hotter, more massive, and significantly more luminous than our Sun, creating an intense radiation environment for any close-orbiting planet. WASP 112's high luminosity and temperature create extreme conditions for WASP 112b. The stellar spectrum is shifted toward higher energies, more UV radiation driving vigorous atmospheric photochemistry and heating. The star's youth means it was even more active in the past, with stronger magnetic fields and potentially more intense radiation that might have contributed to the planet's current inflated state. F-type stars are particularly interesting hosts for studying extreme, hot Jupiter physics. WASP 112b orbits at just 0.0294 AU, about 4.4 million kilometers, or less than 3% of Earth's distance from the Sun. At this proximity to such a luminous star, the radiation is overwhelming. This intense radiation has profound effects. It heats the observable atmosphere to temperatures where molecules dissociate into atoms. It drives powerful winds at several kilometers per second. And most importantly, it somehow transports energy deep into the planet's interior, hundreds or thousands of kilometers below the visible surface, heating the planet from within and causing it to expand like a hot air balloon. WASP 112b is classified as an inflated hot Jupiter, a gas giant that has expanded far beyond what gravity alone would allow. WASP 112b is one of the most inflated hot Jupiters we know. At 1.88 Jupiter radii with 0.88 Jupiter masses, its density is extraordinarily low, 0.16 g/cm superscript 3. For comparison, Saturn has 0.69 g/cm superscript 3, and even extremely inflated planets like WASP 107b have similar densities. WASP 112b is at the extreme end of inflation. Understanding what makes it so puffy tests our theories of planetary structure and atmospheric heating mechanisms. Hot Jupiter inflation has puzzled astronomers for decades. Standard models predict that Jupiter-mass planets should be roughly Jupiter-sized regardless of temperature. Gravity should compress them. Yet planets like WASP 112b are nearly twice Jupiter's size. Something is preventing gravitational contraction. Proposed inflation mechanisms. 1. Stellar irradiation, opacity-driven. High atmospheric opacity traps stellar radiation, transporting heat downward through radiation or convection into the deep interior, where it prevents cooling and contraction. 2. Ohmic dissipation. Atmospheric winds interacting with the planet's magnetic field generate electrical currents that dissipate as heat throughout the interior. 3. Kinetic energy deposition. Breaking atmospheric waves, like ocean waves crashing on a beach, deposit kinetic energy as heat in the deep interior. 4. Tidal heating. Orbital eccentricity causes tidal flexing, generating internal heat. Less relevant for WASP 112b given near circular orbit. 5. Double diffusive convection. Composition gradients inhibit normal convection, allowing heat to accumulate in specific layers and preventing efficient cooling. For WASP 112b, receiving 2,400 times Jupiter's stellar flux, stellar irradiation is almost certainly the dominant inflation mechanism. But exactly how energy is transported from the hot dayside atmosphere down into the deep interior, perhaps 500,100 kilometers deep, where temperatures and pressures are enormous, remains uncertain. Multiple mechanisms might operate simultaneously. WASP 112b's extreme inflation suggests these mechanisms are operating at high efficiency. Modeling WASP 112b's interior requires accounting for the energy deposition that prevents contraction. Interior structure. Atmosphere. Hot hydrogen and helium-dominated atmosphere. Temperature decreases from 1,800 K at observable levels to 1,500 K deeper. Contains trace molecules and atoms from photochemistry. Envelope. Molecular hydrogen transitions to atomic hydrogen, then metallic hydrogen. Temperature increases from 1,500 K to 5,000 to 10,000 K. Energy deposition from stellar heating occurs throughout this region, maintaining high internal temperature. Core. Small rocky icy core, possibly 5 to 15 Earth masses. Temperature perhaps 10,000 to 20,000 K. The core's exact mass is uncertain, but must be small enough that the planet remains extremely inflated. The key to WASP 112b's inflation is that stellar energy continuously adds heat throughout the interior faster than the planet can radiate it away. The planet reaches a thermal equilibrium where it's much larger than it would be without the continuous energy input. It's like keeping a hot air balloon inflated by constantly adding heat. Turn off the heat source, and it would deflate over millions of years. WASP 112b's large size and bright host star make it an excellent target for atmospheric characterization through transmission spectroscopy. We've observed WASP 112b using Hubble Space Telescope and ground-based telescopes to obtain transmission spectra, measuring how the planet's atmosphere absorbs starlight at different wavelengths during transits. The large atmospheric scale height, about 900 kilometers, means spectral features are stronger than on compact planets, making atmospheric species easier to detect. Observations have detected or inferred several atmospheric constituents in WASP 112b's hot atmosphere. There are many key atmospheric detections. Sodium. Strong detection in optical spectrum. At 1,800 K, sodium exists as atomic vapor. The wings of the sodium D lines are broad, indicating high temperature and pressure broadening. Potassium, detected at 770 nanometers, though weaker than sodium, confirms high-temperature conditions where alkali metals are important opacity sources. Water vapor, evidence for water absorption features in near-infrared, though partially muted by clouds or hazes. At 1,800 K, water is thermally stable but might be partially dissociated on the hottest day side. Hydrogen and helium, dominant atmospheric constituents, as expected, inferred from mean molecular weight and atmospheric properties. Possible titanium oxide and vanadium oxide. Some observations hint at TO and VO absorption in optical spectrum, though not definitive. If present, these species could create temperature inversions. High-altitude hazes or clouds. Spectral slope and muted features indicate presence of aerosols at high altitudes, possibly silicate clouds or photochemical hazes. WASP. 112b's atmosphere shows typical hot Jupiter features, sodium, potassium, water vapor, but with some cloudiness or haziness that mutes the spectral features. The presence or absence of TO/VO is crucial because these molecules can create temperature inversions by absorbing optical and UV radiation. Definitively detecting or ruling out TO/VO on WASP 112b would help understand which hot Jupiters develop inversions and which don't. While transmission spectroscopy probes the atmosphere's edge, eclipse observations measure thermal emission from the planet's dayside, revealing temperature and heat distribution. The dayside temperature measurement tells us about atmospheric circulation efficiency. If heat redistribution were perfect, day and night would be the same temperature, about 1,800 K. If there were no redistribution, the day side would be much hotter and the night side nearly 0 K. WASP 112b shows moderate redistribution. The day side is hot, 100 K, but not as extreme as it could be, indicating substantial but imperfect heat transport by winds. WASP 112b's atmosphere is in constant violent motion, driven by the extreme day-night temperature contrast and tidal locking. Our circulation models for WASP 112b predict dominant eastward equatorial jet streams reaching 4 to 6 kilometers per second, well above the speed of sound in the atmosphere. These supersonic winds transport heat from the 2,100 K day side toward the cooler night side. The hot spot, the warmest region, is offset eastward from the substellar point by perhaps 30 to 50 degrees due to wind advection, consistent with what we observe in phase curves of similar planets. The winds aren't just horizontal. Vigorous vertical motions create updrafts on the day side, rising kilometers in minutes, and downdrafts on the night side, bringing cooler gas downward. This three-dimensional circulation mixes the atmosphere, affecting cloud formation, chemical distribution, and energy transport throughout the planet. WASP 112b's temperature structure determines chemistry, cloud formation, and energy balance. WASP 112b presents radically different conditions across its surface. The day side, 2,000 to 2,200 K, glowing hot from stellar radiation and thermal emission. Molecules partially dissociated, atomic H, Na, K dominate upper atmosphere. Strong updrafts and intense UV exposure. Possible silicate clouds evaporating. Extreme stellar radiation continuously heating. The night side, 1,200 to 1,500 K estimated. Cooler, but still extremely hot by terrestrial standards. Molecules can reform, water, CO, CH4, though methane unlikely at these temperatures. Downdrafts bringing gas from high altitude. Clouds more likely to form and persist. Heat radiated to space more efficiently. The terminators, day-night boundaries. Sharp temperature gradients. Strong vertical mixing. Complex chemistry as molecules form/dissociate. Winds converging from dayside flow. The day-night circulation on WASP 112b creates a dynamic, constantly evolving atmospheric state. Gas heated on the day side expands and flows toward the night side at high speed. It cools and contracts on the night side, then returns at lower altitudes. This creates complex, three-dimensional flow patterns with vortices, jets, and turbulence unlike anything in our solar system. WASP 112b's extreme inflation makes it ideal for testing which heating mechanisms are most effective. We've run detailed models of WASP 112b's thermal evolution, trying to reproduce its observed radius. Standard irradiation-only models, where stellar radiation is simply deposited at the surface, can't inflate the planet enough. We need to invoke deeper energy deposition. Models with ohmic dissipation from magnetic fields interacting with winds or kinetic energy deposition from breaking waves can reproduce the observed inflation if the energy reaches depths of 500,000 kilometers. WASP 112b is telling us that these exotic mechanisms must be operating. Understanding WASP 112b's inflation requires accounting for all energy sources and sinks. The puzzle is that only a fraction of the incident stellar energy, perhaps 10-30%, needs to reach the deep interior to maintain inflation. But getting it there through hundreds or thousands of kilometers of atmosphere is the challenge. Multiple mechanisms working together are likely required. Hot Jupiters show enormous diversity in their degree of inflation, even at similar irradiation levels. WASP 112b represents the extreme end. Hot Jupiter inflation spectrum. Compact, radius 1.0 Jupiter. Examples: WASP 18b hat P2b. High mass and or low irradiation. Gravity compresses planet efficiently. Moderately inflated, radius 1.2-1.5 Jupiter. Examples: HD209 458b, WASP 121b. Standard inflation mechanisms operating. Highly inflated, radius greater than 1.8 Jupiter. Examples: WASP 112b, WASP 79b, KLT 9b. Extreme irradiation and or low mass. Multiple inflation mechanisms at high efficiency. The diversity tells us that inflation depends on multiple factors. Stellar irradiation is important, but so is planetary mass, composition, magnetic field strength, atmospheric metallicity, and possibly even stellar spectral type. WASP 112b's position at the extreme helps us understand the limits. How large can a hot Jupiter get before atmospheric escape begins stripping the envelope faster than it can be replenished? With such intense irradiation and low gravity, 0.25 g, WASP 112b should be experiencing atmospheric escape. This atmospheric escape adds another dimension to understanding WASP 112b's evolution. The planet is not static. It's actively losing mass, and its radius might slowly decrease over millions of years as atmospheric escape competes with ongoing inflation from stellar heating. WASP 112b will remain a high-priority target for atmospheric studies as new capabilities become available. 467 light-years from Earth, WASP 112b continues its orbit. Every 3.4 days, every 82 hours, it completes another circuit around its bright F-type star. The same hemisphere eternally faces the blazing star. The other knows only darkness, though darkness is relative when even the night side glows at 1,300 to 1,500 K. Imagine, if such a thing were possible, approaching WASP 112b. From space, it appears enormous, nearly twice Jupiter's radius. But its mass is similar to Jupiter's, creating a planet so inflated, so insubstantial, that its average density is less than styrofoam. Entering the upper atmosphere, you'd find yourself floating through tenuous hydrogen and helium. The gravity is only 1/4 Earth's, barely holding the extended atmosphere. The temperature climbs rapidly, 1,500 K, 1,800 K, 2,000 K as you descend. On the day side, the star dominates the sky. Enormous and blindingly bright, larger than the sun appears from Earth. The atmosphere glows orange-white from thermal emission. Supersonic winds race eastward at 5 kilometers per second, creating a roar unlike anything in human experience. Clouds might drift at certain altitude levels, not water clouds, but silicate clouds form from vaporized rock or photochemical hazes created by intense UV radiation breaking apart molecules. The sky isn't blue. At these temperatures, it would appear hazy orange-red from scattered light and thermal emission. Deeper still, thousands of kilometers down, hydrogen transitions from gas to liquid to exotic metallic states. Temperature climbs to 5,000 K, 8,000 K, pressure mounts, millions of times Earth's atmosphere pressure. And throughout this region, stellar energy deposited from above maintains temperature high enough to prevent gravitational contraction. The planet stays inflated, swollen by continuous energy input from the blazing star above. At the center, perhaps, lies a small rocky icy core, the seed around which this massive world formed billions of years ago, now buried under thousands of kilometers of hot, inflated gas. WASP 112b has taught us that stellar irradiation can fundamentally alter planetary structure, that with sufficient heating, gas giants can be inflated to nearly twice their natural size, that multiple mechanisms, radiation transport, ohmic dissipation, wave breaking, must work together to achieve such extreme inflation. It has revealed the limits of how large a hot Jupiter can become. WASP 112b sits near the boundary. Much more inflated and atmospheric escape will begin stripping the envelope faster than heating can replenish it. The planet is balanced at the edge of stability. WASP 112b reminds us that planets are dynamic, evolving systems shaped by their environments. That proximity to a star doesn't just heat a planet's surface. It can change the planet's fundamental structure, preventing contraction that gravity demands, creating worlds puffed up like balloons by continuous energy input. This is WASP 112b, the swollen giant, a hot Jupiter inflated to 1.88 times Jupiter's radius by one of the most intense stellar irradiation environments known. A planet with density less than styrofoam, where gravity barely holds the extended atmosphere, and supersonic winds rage through the blazing heat. A reminder that planets can be pushed far beyond their natural state by stellar radiation. That gas giants exist in forms we never imagined before discovering hot Jupiters. And that by studying extremes like WASP 112b, we understand the fundamental physics of how planets respond to intense energy input, knowledge applicable to thousands of similar worlds throughout the galaxy. The research is ongoing. The inflation persists. And through this swollen giant, we see the physics of extreme planetary inflation revealed in its most dramatic form. For our next planet today, let's warp on over to WASP 137b, the twilight giant, and the diversity of hot Jupiter atmospheres. 423 light-years from Earth, in the constellation Triangulum, orbits a world that reminds us that not all hot Jupiters are extremes. WASP 137b, a gas giant roughly Jupiter's mass, but 1.3 times its radius, orbiting its sun-like star every 4.3 days at a distance that places it squarely in the hot Jupiter regime, but not at the scorching extremes. With an equilibrium temperature around 1,550 Kelvin and moderate stellar radiation, WASP 137b represents the typical hot Jupiter, if such a thing can be said to exist. It's neither the hottest nor the coldest, neither the most inflated nor the most compact, neither the closest to its star nor orbiting at the outer edge of the hot Jupiter distribution. Yet this very typicality makes it scientifically valuable. WASP 137b offers a window into understanding the broad middle of the hot Jupiter population, the thousands of worlds that don't make headlines for extreme properties but collectively define what we mean by hot Jupiter. Through studying planets like this, we learn how atmospheric composition, heat distribution, and chemical processes operate under conditions that are extreme by Earth standards yet moderate compared to the most intense hot Jupiter environments. Recent observations have revealed water vapor in its atmosphere, clouds that partially obscure deeper layers, and temperature variations that hint at complex atmospheric dynamics. WASP 137b is teaching us that even ordinary, hot Jupiters harbor extraordinary complexity. By 2014, the wide-angle search for planets had been operating for over a decade, discovering more than 150 planets through the transit method. SuperWASP North, located in the Canary Islands, monitored northern hemisphere stars night after night, accumulating years of observations. WASP 137 was cataloged as 1 SWASP J01365 8.19 plus 31365 3.5, a magnitude 12.4 G-type star triangulum. Between 2004 and 2013, SuperWASP North accumulated thousands of observations. Our automated pipeline detected periodic transit signals every 4.3 days with a depth of approximately 1.2%, indicating a large planet, slightly bigger than Jupiter, in a relatively close orbit. The transit shape and consistency across multiple seasons confirmed it as a strong planetary candidate. The 4.3-day orbital period placed WASP 137b firmly in the hot Jupiter category, close enough to be tidally locked and intensely heated, but not at the ultra-short periods of the most extreme examples. The transit depth suggested a planet moderately inflated beyond Jupiter's size. Confirming WASP 137b and determining its mass required precision radial velocity measurements using high-resolution spectrographs. We used the SOFI spectrograph at Observatoire de Haute-Provence and other instruments to measure WASP 137's radial velocity variations. The star showed a clear wobble with a semi-amplitude of about 130 meters per second, consistent with a Jupiter-mass planet in the orbit indicated by transits. We measured a planetary mass of approximately 1.16 Jupiter masses. Combined with the radius from transits, about 1.33 Jupiter radii. This gave a density of approximately 0.65 G/cm superscript 3, similar to Saturn's density. The discovery was announced in 2015 as part of a larger catalog of WASP planets. WASP 137b joined the growing population of hot Jupiters, notable not for any single extreme property, but for representing the broad middle of the population, the typical case against which extremes are measured. WASP 137 is a G-type star, similar in many respects to our Sun, creating a familiar stellar environment for its close-orbiting planet. WASP 137's similarity to the Sun makes it particularly interesting for comparative studies. When we observe WASP 137b, we're essentially seeing what would happen if Jupiter were moved inward to a 4.3-day orbit around our Sun. The stellar spectrum, activity level, and radiation output are all very similar to what the Sun provides, allowing us to isolate the effects of orbital distance on planetary properties without the complication of different stellar types. WASP 137b orbits at approximately 0.0525 AU, about 7.9 million kilometers from its star, roughly 5 times closer than Mercury orbits the Sun. At this distance, the stellar irradiation is intense, but not extreme compared to the hot Jupiters. This moderate irradiation places WASP 137b in an interesting regime. It's hot enough to be tidally locked, to have a predominantly atomic rather than molecular upper atmosphere, and to experience significant inflation. But it's not so hot that exotic chemistry dominates, or that atmospheric escape is extreme. WASP 137b represents the sweet spot for studying typical hot Jupiter atmosphere processes. WASP 137b is classified as a hot Jupiter with moderate inflation, larger than Jupiter but not approaching the most extreme cases. WASP 137b's moderate inflation, 33% larger than Jupiter despite having similar mass, is typical for hot Jupiters receiving this level of stellar irradiation. The density of 0.65 g/cm superscript 3 is similar to Saturn's, showing that stellar heating has caused some expansion, but not the extreme inflation seen in planets receiving 10 to 20 times more flux. WASP 137b demonstrates the normal response of a gas giant to moderate stellar heating. WASP 137b's 33% radius increase compared to Jupiter requires explanation. Standard cold evolution models predict Jupiter mass planets should be Jupiter-sized. The additional radius comes from stellar heating preventing efficient cooling and contraction. Heating mechanisms for WASP 137b. Stellar irradiation. Primary mechanism. Approximately 560 times Jupiter's flux absorbed in atmosphere. Some energy transported to deeper layers, maintaining higher interior temperature than cold models predict. Ohmic dissipation possible. Atmospheric winds interacting with planetary magnetic field might generate electrical currents that dissipate as heat. Efficiency uncertain, but could contribute to inflation. Tidal heating minimal. Near circular orbit means minimal tidal heating from eccentricity. Not a major contributor for WASP 137b. For WASP 137b, stellar irradiation alone is likely sufficient to explain the observed inflation. The moderate flux level produces moderate inflation, a direct demonstration of how stellar heating scales with irradiation intensity. WASP 137b's internal structure follows the standard gas giant pattern, but with elevated temperatures from stellar heating. Atmosphere, top few hundred km. Hot hydrogen-helium atmosphere. Temperature decreases from 1,550 K at observable levels to 1,300 K deeper. Contains molecular species like water, carbon monoxide, methane, depending on altitude and temperature. Envelope, hundreds to thousands of km. Molecular hydrogen transitions to atomic hydrogen, then metallic hydrogen with increasing depth. Temperature rises from 1,300 K to 5,000 to 8,000 K. Stellar heating maintains temperatures somewhat elevated compared to isolated planet. Core. Heavy element core, possibly 10 to 20 Earth masses of rock and ice. Temperature perhaps 10,000 to 15,000 K. Core mass typical for gas giants formed through core accretion. WASP 137b's moderate size, bright host star, and favorable orbital inclination make it accessible for atmospheric characterization. We've observed WASP 137b using ground-based telescopes and space-based facilities to obtain transmission spectra. The atmospheric scale height, about 500 kilometers, is moderate, making spectral features detectable but requiring high signal-to-noise observations. We've accumulated sufficient data to detect several atmospheric species and characterize the overall atmospheric structure. Observations have detected or inferred multiple atmospheric constituents in WASP 137b's hot atmosphere. Water vapor. Clear detection of water absorption features in the near-infrared spectrum at 1.4 microns and other wavelengths. Water is thermally stable at WASP 137b's temperature and is among the most abundant molecules after hydrogen and helium. Sodium. Detection of sodium absorption in optical spectrum. The sodium D lines show both core and pressure-broadened wings, indicating substantial sodium vapor at high altitudes. Potassium. Tentative detection at 770 nanometers. Potassium is expected to be present alongside sodium at these temperatures. Hydrogen and helium. Dominant atmospheric constituents, as expected for gas giants, inferred from overall atmospheric properties and mean molecular weight. Carbon monoxide. Expected to be present based on equilibrium chemistry at 1,550 K, though direct detection requires higher spectral resolution than achieved so far. Clouds or hazes. Evidence for high-altitude aerosols that partially obscure the deeper atmosphere. Spectral features are muted compared to cloud-free models, indicating patchy cloud coverage or hazes. WASP. 137b's atmosphere shows the typical hot Jupiter composition: water vapor, sodium, hydrogen, helium, but with moderate cloud coverage that partially obscures molecular features. The clouds aren't thick enough to completely flatten the spectrum like on some planets, but they do reduce feature amplitudes by perhaps 30 to 50%. This intermediate cloudiness is actually quite common among hot Jupiters, neither perfectly clear nor completely opaque. At 1,550 K, certain cloud species can form in WASP 137b's atmosphere, while others would evaporate. The cloud distribution on WASP 137b is likely complex and patchy, clouds forming on the cooler night side and at specific altitudes, transported by winds, evaporating on the hot day side. This creates a dynamic, time-variable cloud pattern that affects observations depending on which parts of the planet we're viewing. WASP 137b's atmospheric temperature varies dramatically between its permanent day and night sides. Temperature distribution. Day side, approximately 1,700 to 1,900 K at the substellar point. Hottest region likely offset eastward by winds. Strong UV exposure drives photochemistry. Minimal cloud coverage due to high temperatures. Night side, approximately 1,200 to 1,400 K estimated. Cooler, but still extremely hot by terrestrial standards. Clouds more likely to form and persist. Reduced photochemistry in the darkness. Terminators, day-night boundaries. Sharp temperature gradients. Complex chemistry as molecules form on night side, dissociate on day side. Vertical mixing and horizontal winds converge. Heat redistribution efficiency. Moderate. WASP 137b's atmosphere transports some heat from day-night, but not perfectly. Day-night temperature difference of 500-700 K suggests partial heat redistribution. WASP 137b's atmosphere is in constant motion, driven by the extreme temperature contrast between its permanent day and night sides. Our circulation models for WASP 137b predict dominant eastward equatorial jet streams reaching 3 to 5 kilometers per second. These winds transport heat from the hot day side toward the cooler night side. The models also predict vertical motions, updrafts on the day side, downdrafts on the night side, and complex three-dimensional flow patterns, including vortices at higher latitudes. WASP 137b's moderate irradiation level produces wind speeds that are strong but not as extreme as on the hottest planets. These powerful winds have multiple effects. They transport heat, moderating temperature extremes. They transport chemical species, creating disequilibrium chemistry as molecules formed in one region are carried to another before they can react to local conditions. And they transport clouds, creating the patchy coverage observed in spectra. At 1,550 K, WASP 137b's atmosphere hosts complex chemistry driven by temperature, photochemistry, and circulation. Key chemical processes. At 1,550 K, Most molecules are thermally stable. Water, carbon monoxide, some methane at depth, and various metal-bearing molecules exist. Equilibrium chemistry determines abundances at each pressure-temperature level. UV radiation from the star breaks apart molecules in the upper atmosphere, creating radicals and enabling reactions that wouldn't occur in dark conditions. Photochemistry creates photochemical hazes and alters atmospheric composition at high altitudes. Rapid vertical and horizontal mixing transports gas between regions with different temperatures faster than chemistry can equilibrate. This creates disequilibrium abundances, molecules present at levels different from local equilibrium predictions. Molecules formed on the cool night side are transported to the hot day side where some dissociate. Species formed in day-side photochemistry are transported to the night side. This creates hemispheric chemical differences. WASP 137b's properties place it squarely in the middle of the hot Jupiter distribution, neither extreme nor unusual, but representative of the most common type. WASP 137b is what we might call a standard hot Jupiter. If we averaged all hot Jupiter properties, we'd get something close to WASP 137b. This typicality is scientifically valuable. Extreme cases teach us about boundary conditions, but typical cases like WASP 137b teach us about the common physics and chemistry that govern most hot Jupiter atmospheres. Understanding WASP 137b means understanding thousands of similar planets. In science, extreme cases often capture attention. The hottest, the largest, the most unusual planets. But understanding the typical cases is equally crucial. Why WASP 137b matters. 1. Defines the baseline. Extreme cases are only recognizable as extreme if we know what's typical. WASP 137b helps establish the baseline hot Jupiter properties. 2. Tests general theories. Theoretical models must explain both extremes and typical cases. WASP 137b tests whether models work for the common case, not just edge cases. 3. Represents the majority. Most hot Jupiters are like WASP 137b, moderate properties, moderate irradiation. Understanding them means understanding the majority of the population. 4. Reveals scaling relationships. By comparing many similar planets, we can identify how properties scale with parameters like stellar flux, planetary mass, or stellar type. Despite being typical, WASP 137b remains an attractive target for JWST atmospheric studies due to its bright host star and favorable properties. WASP 137b is ideal for JWST observations because it offers a clean test of our understanding without the complications of extreme properties. We can compare observations to models developed for typical hot Jupiters and see if our theoretical understanding is correct. If we can't accurately model WASP 137b, which is moderate in all respects, it means our fundamental understanding of hot Jupiter atmospheres needs revision. Every observation of WASP 137b contributes to a larger effort to understand hot Jupiter atmospheres across their full range of properties. By observing many hot Jupiters, some like WASP 137b, others more extreme, astronomers can identify which properties depend on stellar irradiation, which on planetary mass, which on atmospheric composition, and which on other factors. Statistical studies of hot Jupiter populations reveal trends. WASP 137b, as a typical member, helps define these trends and identify outliers. Theoretical atmospheric models must reproduce observations of planets like WASP 137b to be considered successful. Each new observation refines and tests these models. 423 light-years from Earth, WASP 137b continues its orbit. Every 4.3 days, every 104 hours, it completes another circuit around its sun-like star. One hemisphere eternally faces the star, heated to 1,700 to 1,900 K. The other knows perpetual night, cooler but still blazing at 1,200 to 1,400 K. Imagine approaching WASP 137b. From space, it appears about one-third larger than Jupiter, noticeably inflated but not grotesquely so. Closer, you see atmospheric structure, bands of clouds, regions of clear atmosphere, the complex interplay of chemistry and dynamics. Entering the upper atmosphere, you'd find temperatures around 1,550 K, hot enough to vaporize rock, but cooler than the most extreme hot Jupiters. The atmosphere isn't perfectly clear. Patches of clouds drift at various altitudes, formed from condensed minerals. Water vapor molecules float alongside hydrogen and helium, with sodium and potassium atoms adding their signature to the atmospheric composition. The winds aren't as extreme as on the hottest planets, only 3 to 5 kilometers per second rather than 7 or 8. But they're still supersonic, racing eastward in powerful jet streams that transport heat from the scorching day side toward the cooler night side. On the permanent day side, the star hangs motionless in the sky, similar in appearance to our sun, but providing vastly more heat at this proximity. The sky wouldn't be blue. At these temperatures, it would appear hazy orange or red from scattered light and thermal emission. Clouds might the horizon, silicate particles drifting through the hot air. Deeper still, the atmosphere transitions from molecular to atomic hydrogen, then to metallic hydrogen thousands of kilometers down. Temperature and pressure climb steadily. At the center lies a heavy element core, perhaps 10 to 20 Earth masses of rock and ice, the seed around which this gas giant formed billions of years ago. WASP 137b has taught us that typical doesn't mean boring or unimportant, that the middle ground of the hot Jupiter population harbors the same complex atmospheric processes, the same intricate chemistry, the same dynamic weather patterns as the extremes, just at moderate levels that may be more representative of what most planets in the galaxy experience. It has shown us that understanding planetary atmospheres requires studying the full population, not just the extremes that capture headlines, but the typical cases that define what we mean by hot Jupiter. Water vapor detected in its atmosphere, clouds partially obscuring deeper layers, supersonic winds transporting heat and chemicals, all operating at the moderate intensity that characterizes thousands of similar worlds. WASP 137b reminds us that science advances through understanding both the exceptional and the ordinary, that statistical majorities matter as much as individual extremes, that the planet which best represents the average is, in its own way, as scientifically valuable as the most unusual outlier. This is WASP 137b, the Twilight Giant, a hot Jupiter with moderate properties that place it squarely in the middle of the population, 1.3 times Jupiter's radius, 1,550 K temperature, 4.3-day orbit around a sun-like star. Neither the hottest nor the coolest, neither the most inflated nor the most compact. Simply typical. A reminder that understanding the universe requires studying not just the extremes but the middle ground, that the most common cases define the norm from which extremes deviate, and that by understanding planets like WASP 137b, the standard, the typical, the representative, we understand what hot Jupiters fundamentally are across thousands of worlds throughout the galaxy. The observations continue. The planet orbits on, and through this moderate, typical, yet endlessly complex world, we see the diversity and unity of hot Jupiter atmospheres throughout the cosmos. If you enjoy the hope for life, get ready for the neighboring world of GJ15AB and the search for nearby habitable planets. 11.6 light-years from Earth. In cosmic terms, this is our immediate neighborhood. So close that light from this system left before you started reading this sentence and will arrive before you finish this paragraph. The star is GJ-15a, also known as Groombridge 34a, a red dwarf visible from Earth with binoculars. And orbiting this nearby star is a world that has captured the attention of astronomers searching for potentially habitable planets. GJ-15ab. Discovered in 2014 through patient radial velocity observations, GJ-15ab is a super-Earth, a planet with at least 3 times Earth's mass, orbiting within or near the habitable zone of its cool red dwarf star. Its proximity, combined with its favorable position and properties, makes it one of the highest priority targets for future atmospheric characterization and the search for biosignatures on nearby worlds. GJ-15ab represents a crucial milestone in the search for habitable worlds. It's not just another exoplanet among thousands. It's one of the closest potentially habitable planets ever discovered, orbiting a star near enough that with future technology, we might directly image its atmosphere, search for signs of life, or even consider it as a target for interstellar probes. The planet that might be habitable, practically in our cosmic backyard. Finding planets around nearby stars has been a priority for decades. Nearby planets are brighter, easier to study, and more accessible for future missions. Red dwarf stars, cool, small, long-lived, are particularly attractive targets because they're the most common stellar type and their habitable zones are close in, making planets easier to detect. GJ-15a was a natural target for our radial velocity surveys. At only 11.6 light-years away, it's among the 30 closest stellar systems to Earth. It's a quiet M1.5 dwarf, relatively inactive compared to many red dwarfs, making radial velocity measurements more reliable. Between 2011 and 2014, we accumulated dozens of high-precision radial velocity measurements using multiple instruments including HARPS, HIRES, and PFS. The data revealed a clear periodic signal with a period of 11.4 days and a semi-amplitude of about 2.5 meters per second. A radial velocity semi-amplitude of 2.5 meters per second is subtle, about walking speed, but detectable with modern precision spectrographs. The 11.4-day period and radial velocity amplitude indicated a planet with a minimum mass of approximately 3.03 Earth masses orbiting at about 0.072 AU from the star. The discovery was announced in 2014, though the planet had been tentatively identified in earlier data. GJ-15a immediately joined the ranks of the closest known potentially habitable exoplanets. Confirming planets around red dwarfs is complicated by stellar activity. Star spots, flares, and magnetic cycles create radial velocity variations that can mimic or obscure planetary signals. For GJ-15a, we had to carefully analyze the stellar activity signals versus the planetary signal. We monitored stellar activity indicators, chromospheric emission, photometric variations, and found that GJ-15a is relatively quiet for an M-dwarf, with a rotation period of about 44 days. The 11.4-day planetary signal is distinct from the stellar rotation period and other activity timescales, giving us confidence it's a genuine planet rather than an activity-induced false positive. After years of observations ruling out alternative explanations, GJ-15ab was confirmed as a genuine super-Earth orbiting one of our nearest stellar neighbors. GJ-15a, also cataloged as Groombridge 34a, is an M-dwarf red dwarf star, one of billions in the galaxy but special for being so close to Earth. GJ-15a's proximity is its most important characteristic for exoplanet studies. At 11.6 light-years, it's closer than famous stars like Tau Ceti or Epsilon Eridani. This proximity means any planets orbiting GJ-15 receive more photons from our perspective, making them brighter and easier to study than similar planets around more distant stars. For atmospheric characterization and future direct imaging, proximity is everything. GJ-15A is not alone. It has a binary companion, GJ-15b, orbiting at a wide separation. The wide separation means GJ-15b has negligible gravitational influence on GJ-15ab. The planet orbits in essentially a single star environment, with the distant companion appearing as a faint red dot in the sky. GJ-15ab is classified as a super-Earth based on its mass, though without transit observations, many properties remain uncertain. With only radial velocity data, we know GJ-15ab's minimum mass and orbit, but not its radius or density. At 3 to 4 Earth masses, it could be a rocky super-Earth with at most a thin atmosphere, a water world with a substantial water/ice layer, or even a small volatile-rich planet with a thick envelope. The composition determines habitability. Rocky or water-rich planets could potentially host life, while volatile-rich mini-Neptunes probably cannot. GJ-15ab's most significant characteristic is its position in or very near the habitable zone, the region where liquid water could exist on a planet's surface with the right atmospheric conditions. GJ-15ab's position is nearly ideal. It receives about 1.4 times Earth's solar flux, enough to be warm and potentially temperate, but not so much that runaway greenhouse effects are inevitable. If GJ-15ab is rocky with a moderate atmosphere, liquid water oceans could exist. The planet sits right where we'd want to look for potentially habitable worlds around M dwarfs. Without knowing the radius, scientists model possible internal structures based on the measured mass and formation theories. Scenario 1. Rocky super-Earth with thin atmosphere. Composition: iron silicate core and mantle similar to Earth but larger. Potentially habitable. Rocky surface, moderate atmosphere, possible liquid water. Scenario 2. Water world. Composition: rocky core with massive water/ice layer. Potentially habitable if water remains liquid at depth despite high pressure. Scenario 3. Mini-Neptune. Composition: rocky core with thick hydrogen-helium envelope. Unlikely to be habitable. No accessible liquid water. Extreme atmospheric conditions. Mass-radius relationships suggest that at 3 to 4 Earth masses, GJ-15ab is most likely either a rocky super-Earth or a water-rich world. Mini-Neptune composition becomes more common above 5 Earth masses. Given the planet's position in the habitable zone and the host star's metal pore composition, scenarios 1 or 2, rocky or water world, seem more plausible. But we need the radius to know for certain. Despite many uncertainties, GJ-15ab shows several characteristics favorable for potential habitability. GJ-15a is 3 to 8 billion years old, past the high-activity youth of M dwarfs. Lower flaring than younger M dwarfs reduces atmospheric erosion risk. GJ-15ab checks many boxes for habitability. It's in the right place, the right mass, around a suitable star. The proximity is crucial. This isn't some distant world we'll never study in detail. GJ-15ab is close enough that within our lifetimes, we might be able to search its atmosphere for biosignatures. That makes it one of the most important, potentially habitable planets discovered. Despite favorable conditions, GJ-15ab faces challenges common to M-dwarf planets, and critical information remains unknown. At 0.072 AU around an M-dwarf, almost certainly tidally locked, one side always faces star, creates extreme day-night temperature contrast without sufficient atmosphere to redistribute heat. Even relatively quiet M-dwarfs produce flares. High-energy radiation could erode atmospheres, especially when the star was younger and more active. Without transits, we don't know if it's rocky, water-rich, or has thick envelope. Composition determines habitability. No atmospheric detection yet. Planet might be airless, have thin atmosphere, or a thick atmosphere. Fundamentally affects habitability. M-dwarf spectrum peaks in near-infrared. Earth-type photosynthesis evolved for visible light. Life would need to adapt to red/infrared-dominated illumination. Young M-dwarfs are extremely active. GJ15A likely had intense flaring in its first billion years, potentially stripping early atmospheres. The biggest unknown is the atmosphere. If GJ15AB retained or developed a substantial atmosphere, nitrogen, oxygen, water vapor, CO2, it could be genuinely habitable despite tidal locking and M-dwarf challenges. If it lost its atmosphere early or never developed one, it's probably barren. We need observations to answer this fundamental question. For decades, tidal locking was considered fatal to habitability. Modern climate modeling has challenged this view. If GJ15AB has an atmosphere with surface pressure above about 0.1 bar, 1/10 Earth's pressure, atmospheric circulation can redistribute heat efficiently. Winds transport heat from the permanent day side to the permanent night side, creating moderate temperatures across much of the planet. Computer models show that with Earth-like atmospheric pressure, even tidally locked planets can have habitable climates with liquid water oceans on the day side, and perhaps globally. On GJ15AB, if it has an atmosphere, the star would hang motionless in the dayside sky, a dim red sun, smaller than Earth's sun, but providing similar total energy. The day side would experience eternal day, the night side eternal night. At the terminator, the permanent twilight zone, conditions might be most temperate, with perpetual sunset or sunrise creating unique habitats if life exists. The most direct way to characterize GJ15AB would be observing transits. Unfortunately, the geometric probability that it transits is low. This means characterizing GJ15AB's atmosphere requires alternative methods, techniques that don't rely on transits. Without transits, astronomers must use more challenging techniques to study GJ15AB. Alternative approaches. 1. Reflected light spectroscopy. Detect the planet's reflected starlight separated from the much brighter star. Requires extremely high contrast imaging. Could detect atmospheric molecules, surface properties, even biosignatures. Future extremely large telescopes, YLTs, or space missions like HWO might achieve this. 2. Thermal phase curves. Measure infrared brightness variations as the planet orbits, detecting its thermal emission. Could constrain temperature, atmospheric heat redistribution. Possible with JWST in principle, though challenging for non-transiting planets. 3. High-resolution spectroscopy. Use Doppler shifts to separate planetary atmospheric absorption from stellar spectrum during the planet's orbit. Works without transits. Future ELTs, GMT, TMT, YLT, might detect molecules in GJ15AB's atmosphere directly. 4. Direct imaging future missions. Separate the planet's light from the star using coronagraphs or star shades. Obtain spectrum revealing atmospheric composition, temperature, surface properties. Habitable Worlds Observatory, 2040s, designed specifically for this. 5. Astrometry. Measure tiny wobble in the star's position on the sky caused by the planet's gravity. Could determine exact mass and orbital inclination. Future Gaia data, releases, or dedicated astrometry missions. Despite the challenges, GJ-15AB remains a high-priority target for current and upcoming observatories. Refine orbital parameters, search for additional planets in the system, improve mass measurement precision. Attempt to detect the planet's thermal emission in infrared during its orbit. If successful, could constrain temperature and atmospheric heat redistribution. Continue searching for transits in case orbital precession or previous non-detections were unlucky timing. Large ground-based telescopes might attempt to detect atmospheric absorption during the planet's orbit using Doppler technique. The 2030s will see the operation of extremely large telescopes with 30 to 40-meter mirrors, transformative for studying nearby planets. Detect atmospheric molecules directly through Doppler-shifted absorption lines. Could detect O2, H2O, CH4, CO2, major biosignatures if present. With advanced adaptive optics and coronagraphs, might directly image GJ-15AB as a point of light separate from a star. Extremely challenging, but potentially feasible for closest planets. If imaged, obtain spectrum revealing atmospheric composition, temperature, possibly surface properties. GJ-15AB is one of the best targets for YLTs. The proximity, 11.6 light-years, means maximum brightness for the planet. Even without transits, YLTs might detect reflected light or thermal emission and characterize the atmosphere. We're designing instruments specifically for planets like this, nearby, potentially habitable worlds around cool stars. The ultimate goal is a dedicated space telescope designed to directly image Earth-like planets around nearby stars, the Habitable Worlds Observatory. For GJ-15AB, HWO could provide definitive answers. Is it rocky or water-rich? Does it have an atmosphere? What molecules are present? Are there biosignatures, oxygen and methane together, for instance, indicating possible life? Within 2 or 3 decades, we might know. GJ-15AB belongs to an exclusive group, the potentially habitable planets closest to Earth. Among these nearby worlds, GJ-15AB stands out for receiving stellar flux very similar to Earth's, being around a relatively quiet M-dwarf, and being accessible to multiple future observation techniques. It's one of the handful of planets within 20 light-years that we'll be able to study in extraordinary detail over coming decades. GJ-15AB is central to one of astrobiology's most important questions. Can planets around M-dwarfs be habitable? M-dwarfs are 75% of all stars in the galaxy. Nearly every M-dwarf has planets, and many have planets in their habitable zones. If M-dwarf planets can be habitable, if tidal locking, stellar activity, and red light aren't deal-breakers, the number of potentially habitable worlds in the galaxy is enormous. GJ-15AB is one of our best opportunities to answer this question through observations rather than theory. If GJ-15AB is found to be habitable, or even more significantly, inhabited, it would suggest billions of M-dwarf planets throughout the galaxy could harbor life. The implications for the frequency of life in the universe would be profound. At 11.6 light-years, GJ-15AB is close enough to be considered, however speculatively, as a target for future interstellar probes. Light-sail spacecraft accelerated by laser to 20% light speed could reach GJ-15A in 58 years. Though initially targeting Alpha Centauri, nearby systems like GJ-15A are alternative candidates. While highly speculative, the proximity means that if GJ-15AB is found to be habitable or shows signs of life, humanity could conceivably send a probe within a human lifetime using technologies being developed today. The planet is close enough to dream about visiting. 11.6 light-years from Earth, GJ-15AB continues its orbit. Every 11.4 days, every 274 hours, It completes another circuit around its red dwarf star. If it's tidally locked, one hemisphere eternally basks under the dim red sun, while the other knows only the faint glow of distant stars. What does GJ-15AB look like? We don't know yet. Is it a rocky super-Earth with continents and oceans, nitrogen skies and water vapor clouds? Is it a water world, a global ocean hundreds of kilometers deep beneath a steamy atmosphere? Or is it something else entirely? A mini Neptune with no solid surface, or a barren rock that never developed an atmosphere? All are possible. All await discovery. We know GJ-15AB is real. We know its mass, its orbit, its location in the habitable zone. We know it receives stellar energy similar to Earth's. But we don't know its radius, its density, whether it has an atmosphere, or whether conditions allow liquid water. Within the next 2 decades, we might know. YLTs might detect its atmosphere through high-resolution spectroscopy. JWST might measure its thermal emission. And within 3 decades, the Habitable Worlds Observatory might directly image it, revealing its true nature. GJ-15AB reminds us that potentially habitable worlds exist in our immediate cosmic neighborhood, that the planets we'll study in the most detail, where we might find life, could be close enough to reach with patient observations and careful analysis, that one of our nearest stellar neighbors might harbor a world not too different from Earth. One of the highest priority targets for every future mission. One of the closest potentially habitable planets. One of the best candidates for finding life beyond Earth. All of this, orbiting a star you could see with binoculars on a clear night if you knew exactly where to look. This is GJ-15AB, the neighbor's world. A super-Earth in the habitable zone of a nearby red dwarf, receiving Earth-like stellar energy, possibly rocky, possibly with oceans and atmosphere. Only 11.6 light-years away, close enough to study, close enough to dream about. A reminder that potentially habitable worlds exist nearby, waiting to reveal their secrets. That the question, are we alone, might be answered by studying planets practically in our cosmic backyard, and that the neighbor's world might be the one where we first detect signs of life beyond Earth. The research is ongoing. The planet orbits on, and someday, perhaps soon, we will know what kind of world GJ-15AB truly is, and whether we're alone in our corner of the galaxy. I hope you're ready to push it to the limit with this next one. K2-187b. The edge of habitability and the boundaries of life-bearing worlds. 993 light-years from Earth, in the constellation Scorpius, orbits a world balanced on a knife's edge. K2-187b, a super-Earth with 1.4 times Earth's radius, receiving approximately 1.8 times the stellar flux Earth receives from the Sun. This places it at the inner edge of the habitable zone, where the greenhouse effect transitions from creating temperate conditions to triggering runaway heating. Is K2-187b a warm but habitable ocean world with stable liquid water beneath clouds? Or has it already crossed the threshold into a Venus-like hell? A runaway greenhouse with scorching temperatures, crushing atmospheric pressure, and oceans long since vaporized? The answer depends on subtle factors we're only beginning to understand. Atmospheric composition, cloud coverage, greenhouse efficiency, and the planet's own geological history. Discovered in 2018 by NASA's K2 mission, K2-187b represents a crucial test case for understanding habitability boundaries. At what stellar flux does a rocky planet transition from potentially habitable to definitively too hot? What atmospheric processes determine this threshold? And what does K2-187b tell us about the inner edges of habitable zones around the billions of similar stars throughout the galaxy? This is the story of a planet at the edge, a world that might help us understand where the limits of habitability lie and what makes the difference between a living world and a dead one. By 2015, the K2 mission had been operating for 2 years, discovering hundreds of planets by observing new fields every 80 days. Campaign 5 targeted a region in Scorpius, monitoring approximately 25,000 stars for planetary transits. K2-187, cataloged as EPIC 2-119-45201, was a magnitude 14.1 K-dwarf star in Scorpius. During the 80-day campaign, K2 accumulated continuous photometric observations. Our planet search pipeline detected periodic transit signals every 20.7 days with a depth of approximately 0.15%, indicating a planet roughly 1.4 Earth radii in size. The period placed it in an interesting regime, long enough to be potentially in or near the habitable zone, which is farther out for cooler K-dwarfs than for the Sun. The transit depth of 0.15% is small, among the shallowest K2 routinely detected, requiring careful analysis to distinguish from stellar variability and instrumental noise. But the signal's consistency across multiple transits confirmed it as a strong planetary candidate. Confirming K2-187b as a genuine planet required eliminating false positive scenarios and, ideally, measuring its mass through radial velocity observations. We use statistical validation techniques to assess the probability that the transit signal was caused by a planet versus false positives like eclipsing binaries or background stars. High-resolution imaging ruled out nearby stellar companions that could create false signals. Analysis of the K2 data showed the transit shape was consistent with a planet rather than a blend. And the host star's characteristics, a relatively bright K-dwarf, made it accessible for radial velocity follow-up, though measuring the mass of a 1.4 Earth radius planet is challenging. Radial velocity observations were attempted, but the planet's low mass and the host star's moderate activity made mass determination difficult. Current best estimates suggest a mass of approximately 2 to 4 Earth masses based on mass-radius relationships, though this remains uncertain. The discovery was announced in 2018 as part of a larger K2 planet catalog, with K2-187b recognized as potentially near the habitable zone's inner edge. K2-187 is a K-type dwarf star, cooler and smaller than the Sun, but larger and hotter than red dwarfs, creating a moderate stellar environment for planets. K2-187's classification as a K3V dwarf places it in an interesting category. It's cooler and less luminous than the Sun, so its habitable zone is closer in, roughly 0.5 to 1.2 AU versus the Sun's 0.95 to 1.5 AU. K2-187b 0.135 AU sits at what we calculate is the inner edge of this habitable zone. The stellar luminosity being 1/3 the Sun's means K2-187b receives similar energy to Earth despite being much closer. The habitable zone, where liquid water could exist on a planet's surface, depends on stellar luminosity and planetary atmospheric properties. For K2-187, calculating this zone reveals K2-187b's critical position. K2-187b is exactly the kind of planet we want to study to understand habitable zone boundaries. It receives 1.8 times Earth's flux, enough to be at risk of runaway greenhouse if conditions aren't right, but potentially still habitable if the atmosphere has the right composition and cloud coverage. This is the transition region where small changes in atmospheric properties can mean the difference between a habitable world and a Venus. K2-187b is classified as a super-Earth based on its size, larger than Earth but smaller than Neptune, placing it in the critical size range where planets transition from rocky to volatile-rich compositions. At 1.4 Earth radii, K2-187b sits right at the radius valley, the boundary between rocky super-Earths and mini-Neptunes with thick volatile envelopes. Statistically, planets this size are usually rocky or water-rich rather than gas-dominated. Combined with its position near the habitable zone inner edge, K2-187b is most likely either a rocky super-Earth with an atmosphere or a water world. The key question is whether that atmosphere is temperate or in runaway greenhouse. K2-187b's fate depends on whether its atmosphere has crossed the threshold into runaway greenhouse heating. The difference between these scenarios depends on subtle factors: initial water inventory, atmospheric composition, cloud properties, and whether the planet crossed the critical threshold where water vapor feedback becomes unstoppable. K2-187b, receiving 1.8 times Earth's flux, sits right at the boundary where either outcome is possible. Understanding K2-187b requires understanding the runaway greenhouse effect, the point of no return where a planet's atmosphere traps so much heat that all water evaporates, creating a self-reinforcing cycle. Climate models suggest the runaway greenhouse threshold for an Earth-like planet is around 1.1 to 1.5 times Earth's solar flux, depending on atmospheric composition and cloud feedback. K2-187b at 1.8 times Earth's flux is likely above this threshold for an Earth-like atmosphere. However, if the planet has very high cloud coverage reflecting much of the stellar radiation, or if it has less water than Earth initially, it might avoid runaway greenhouse and remain habitable. K2-187b tests our understanding of where exactly this threshold lies. Despite receiving 1.8 times Earth's stellar flux, several factors could potentially keep K2-187b habitable. High albedo clouds. If K2-187b has extensive cloud coverage, like Venus, ironically, it could reflect 60 to 80% of stellar radiation, preventing surface overheating despite high incident flux. Low initial water content. If the planet formed with less water than Earth, perhaps forming inside the ice line, limited water vapor would reduce greenhouse feedback intensity. Different atmospheric composition. An N2-dominated atmosphere with less CO2 and H2O than Earth might have weaker greenhouse effect, allowing habitability at higher flux levels. Active plate tectonics. Geological activity regulating atmospheric CO2 through carbonate-silicate cycle could prevent excessive greenhouse buildup. Fortuitous cloud feedback. If warming increases high-altitude reflective clouds more than low-altitude heat-trapping clouds, negative feedback could stabilize temperature. Despite hopeful scenarios, most climate models suggest K2-187b is likely uninhabitable. Stellar flux above model's threshold. 1.8 times Earth's flux exceeds most climate models' inner habitable zone limit of 1.1-1.5 times for Earth-like planets. Likely tidal locking. At 0.135 AU with 20.7-day period, probably tidally locked. Creates extreme day-night temperature gradient that could drive intense atmospheric circulation and water loss. Water vapor escape. High temperatures increase atmospheric water vapor. UV radiation from star can photodissociate H2O in upper atmosphere, with hydrogen escaping to space. Slow but irreversible water loss. Positive feedback dominance. For Earth-like composition, positive greenhouse feedbacks, more water vapor with heat, likely dominate over negative feedbacks, cloud reflection. No magnetic field evidence. Without confirmed magnetic field, stellar wind could erode atmosphere over billions of years, especially for tidally locked planet with one side always exposed. Honestly, K2-187b is probably too hot to be habitable with an Earth-like atmosphere. The 1.8 times solar flux puts it firmly in the Venus zone, the region where runaway greenhouse is likely. However, and this is important scientifically, we don't know this for certain. We haven't directly observed K2-187b's atmosphere. Its possible atmospheric composition or cloud properties we haven't imagined could allow habitability. That uncertainty is why we want to observe planets like this. Astronomers have identified a Venus zone, the region just inside the habitable zone where planets are likely to be Venus-like rather than Earth-like. If K2-187b is indeed Venus-like, it validates climate models predicting where runaway greenhouse occurs. If against expectations it's found to be habitable, it would revolutionize our understanding of habitability limits and potentially expand the habitable zone significantly. K2-187b is scientifically valuable precisely because we're uncertain about its state. Observing its atmosphere. Knowing K2-187b's atmospheric state tells us where the runaway greenhouse threshold lies for K-dwarf systems, applicable to thousands of similar planets. Characterizing K2-187b's atmosphere through transmission spectroscopy faces significant challenges. K2-187b is not an easy target for atmospheric characterization. The faint host star and small planet size work against us. However, if the planet has a thick Venus-like atmosphere, features might be strong enough for JWST to detect with dedicated observations. If it's rocky with thin atmosphere, we probably won't detect anything with current technology. Future missions specifically designed for rocky planet atmospheres, like HabEx or LUVOIR concepts, would have better chances. Studying multiple planets across the habitable zone-to-Venus zone transition allows astronomers to identify patterns and test where the boundary actually lies. K2-187b, receiving relatively high flux, helps define the hot end of this transition. Venus is our local example of what happens when you put an Earth-like planet just inside the habitable zone. K2-187b receives nearly the same stellar flux Venus receives, 1.8 versus 1.9 times Earth's. If K2-187b started Earth-like, it probably underwent the same runaway greenhouse process Venus did. It's likely a Venus analog, thick atmosphere, crushing pressure, scorching temperatures. Venus teaches us that being similar in size isn't enough. You need to be in the right location. Despite observational challenges, K2-187b remains a target of interest for testing Venus zone theories. Potential near-term observations. JWST transmission spectroscopy, low priority but possible. Multiple transit observations could potentially detect thick atmosphere, if Venus-like. Thin habitable atmosphere, probably undetectable. Follow-up radial velocity. Precise mass measurement would constrain density, helping determine if rocky or water-rich. Requires dedicated observing time on large telescopes. Photometric monitoring. Long-term monitoring for transit timing variations could reveal additional planets in system. Stellar characterization. Better understanding of host stars' activity, rotation, and precise luminosity refines habitable zone calculations. Understanding where habitability ends requires dedicated studies of Venus zone planets. Statistical atmospheric surveys. JWST or future missions observing dozens of Venus zone planets to identify patterns in atmospheric properties versus stellar flux. Comparative studies. Observing planets at different distances from inner habitable zone edge, like K2-187b, K2-3d, Kepler 438b, to map where runaway greenhouse transitions occur. Laboratory climate models. Sophisticated 3D climate models using K2-187b and similar planets as test cases to refine runaway greenhouse physics. Future direct imaging. Missions like Habitable Worlds Observatory 2040S+ might directly image reflected light from Venus zone planets, revealing cloud coverage and surface temperature. K2-187b and other boundary case planets are forcing astronomers to refine habitable zone definitions. Traditional habitable zone calculations made assumptions about Earth-like atmospheres and cloud coverage. As we discover more planets near the boundaries, we're learning those assumptions weren't always correct. Some planets might be habitable closer in than we thought if they have very high albedo clouds. Others might be uninhabitable farther out than we thought if they lack greenhouse gases. K2-187b at 1.8 times flux is probably too hot, but the exact threshold, 1.2 times, 1.5 times, 1.7 times, depends on factors we're still measuring. Each boundary planet we study helps calibrate our habitability zone models. 993 light-years from Earth, K2-187b continues its orbit. Every 20.7 days, every 3 weeks, it completes another circuit around its orange dwarf star. One hemisphere, if tidally locked, eternally faces the star. The other knows only darkness. We don't know what K2-187b looks like. Is it a temperate ocean world, defying the odds with high clouds reflecting most stellar radiation? Liquid water somehow persisting despite the intense energy input? Or is it, more likely, a Venus, a scorched world where oceans boiled away billions of years ago, leaving only crushing atmosphere and furnace-like surface? The answer matters, not just for this one planet, but for understanding thousands of similar worlds throughout the galaxy. K2-187b sits at 1.8 times Earth's stellar flux. Somewhere between Earth's 1.0 and K2-187b's 1.8 lies a threshold, the point beyond which runaway greenhouse becomes inevitable, where habitability ends and Venus conditions begin. Finding this threshold defines the true inner edge of habitable zones around billions of stars. If the threshold is at 1.2 times Earth's flux, then K2-187b is far beyond it, definitely a Venus. If the threshold is at 1.7 times, K2-187b barely crosses it, a Venus but just barely. If somehow the threshold is at 1.9 times, K2-187b might, just might, remain habitable against the odds. We're discovering thousands of exoplanets. Many orbit within calculated habitable zones, but not all habitable zone planets are actually habitable. K2-187b reminds us that habitability is not just about distance from a star. It's about atmospheric composition, cloud feedback, greenhouse efficiency, water inventory, geological activity, and factors we're only beginning to understand. Some planets will surprise us, remaining habitable despite high flux. Others will disappoint, runaway greenhouse despite moderate flux. K2-187b at the boundary could go either way, but most likely, it's teaching us that boundaries exist for a reason, and that the universe creates far more Venus worlds than Earth worlds near the inner edges of habitable zones. This is K2-187b, the edge of habitability, a super-Earth receiving 1.8 times Earth's stellar flux, sitting right at the threshold between potentially habitable and definitively too hot. Probably a Venus analog, scorched, crushing, lifeless, but uncertain enough to merit study. A reminder that finding planets in habitable zones is just the first step. Understanding which ones are actually habitable requires observations we're only beginning to make, and that the boundaries between living worlds and dead ones are drawn not by distance alone, but by the complex interplay of atmosphere, star, and planet that makes worlds either homes for life or hostile hellscapes. The observations wait for future instruments. The planet orbits on, and through this world at the boundary, we learn where habitability ends and where careful observations must replace hopeful assumptions. Things are about to heat up with the scorched world of WASP-119b, a world of flames and the extremes of hot Jupiter atmospheres. 830 light-years from Earth, in the constellation Phoenix, orbits one of the most intensely irradiated gas giants ever discovered. WASP-119b, a planet nearly the mass of Jupiter but significantly larger, swollen by intense stellar heating to 1.4 times Jupiter's radius. Its orbital period, just 1.17 days. Every 28 hours, it completes another scorching circuit around its host star, receiving approximately 5,700 times the stellar flux Jupiter received from our Sun. WASP-119b exists in conditions that test the limits of atmospheric stability. Surface winds rage at supersonic speeds. The dayside atmosphere glows at temperatures exceeding 2,000 Kelvin, hot enough to vaporize most metals. The night side, though cooler, remains blazing at over 1,200 Kelvin. This is a world perpetually on fire with thermal energy. WASP-119b has become a crucial laboratory for studying how planetary atmospheres respond to extreme stellar irradiation. What molecules can survive at these temperatures? How do winds redistribute the overwhelming heat? And what are the limits beyond which atmospheric escape begins stripping the planet faster than it can be replenished? This is the story of a scorched world, a planet pushed to the edge of atmospheric survival, revealing the physics of gas giants and the most extreme environments nature creates. By 2011, the wide-angle search for planets had been discovering hot Jupiters for nearly a decade. SuperWASP South, with its wide-field cameras monitoring millions of stars, had accumulated years of observations across the southern sky. WASP-119 was cataloged as 1SWASP J2359-59.51-390630.4, a magnitude 12.3 G-type star in Phoenix. Between 2006 and 2010, SuperWASP South accumulated thousands of observations. Our automated pipeline detected periodic transit signals every 1.17 days with a depth of approximately 1.5%, indicating a very large planet, significantly bigger than Jupiter, in an ultra-short orbit. The extremely short period immediately flagged it as one of the most intensely irradiated hot Jupiters we discovered. The 1.17-day orbital period placed WASP-119b in the extreme hot Jupiter category, closer to its star than any planet in our solar system, and among the shortest known orbital periods. The transit depth suggested significant inflation from intense stellar heating. Confirming WASP-119b and determining its mass required precision radial velocity measurements. We used Corelli at La Silla Observatory and other spectrographs to measure WASP-119's radial velocity over multiple orbits. The short period made observations efficient. We could observe complete orbits in a single night. The measurements revealed a radial velocity amplitude of about 200 meters per second, indicating a planet of approximately 1.13 Jupiter masses. Combined with the large radius from transits, about 1.40 Jupiter radii, this gave a notably low density of approximately 0.51 G/cm superscript 3, even less dense than Saturn. The discovery was announced in 2015, recognized immediately as an excellent target for atmospheric studies due to its large size, short period allowing frequent observations, and extreme irradiation creating dramatic atmospheric effects. WASP-119 is a G-type star similar to our Sun, but slightly larger and more luminous, creating an intense radiation environment for its close-orbiting planet. WASP-119's higher luminosity, twice the Sun's, combined with WASP-119b's ultra-short orbit creates one of the most intense stellar radiation environments known. The star itself is evolving, having expanded from its main sequence size, which increases its luminosity. This combination of a luminous, evolved G-type star and an extremely close planetary orbit produces exceptional heating of the planet's atmosphere. WASP-119b orbits at just 0.0239 AU, about 3.6 million kilometers, roughly 9 times the Earth-Moon distance. At this distance from such a luminous star, the radiation is catastrophic. This extreme irradiation has profound effects. It heats the day-side atmosphere to temperatures where many molecules dissociate into atoms. It drives supersonic winds reaching 6 to 8 kilometers per second. It causes the planet to swell to 40% larger than Jupiter despite having similar mass. And it may be driving atmospheric escape at rates that could significantly alter the planet over millions of years. WASP-119b is classified as a highly inflated hot Jupiter, a gas giant expanded far beyond its natural size by stellar heating. WASP-119b's 40% inflation is significant, but not the most extreme. We've found planets inflated by 80 to 90%. However, at receiving 5,700 times Jupiter's flux, WASP-119b demonstrates how stellar irradiation causes inflation. The extreme heating deposits energy deep in the planet's interior, preventing efficient cooling and contraction. The planet essentially stays puffed up by the continuous energy input from its nearby star. WASP-119b's inflation requires multiple heating mechanisms working together to maintain its enlarged size. 1. Stellar irradiation, primary. 700 times Jupiter's flux absorbed in atmosphere. Energy transported downward through radiation and convection, heating interior and preventing contraction. 2. Ohmic dissipation. Supersonic atmospheric winds interacting with planetary magnetic field generate electrical currents that dissipate as heat throughout the interior, particularly effective at high wind speeds. 3. Kinetic energy deposition. Atmospheric waves breaking in the deep atmosphere, like ocean waves crashing, deposit kinetic energy as heat. High wind speeds create powerful waves. 4. Tidal heating. Nearly circular orbit means minimal tidal heating from eccentricity. Not a major contributor for WASP-119b. For WASP-119b, the extreme stellar irradiation is clearly the dominant mechanism. But getting that energy deep enough into the interior to prevent contraction requires assistance from ohmic dissipation and wave breaking. The combination maintains the planet in its current inflated state. WASP-119b's interior is shaped by the extreme thermal environment it endures. Atmosphere. Hot hydrogen-helium atmosphere, dominated by atomic species rather than molecules due to extreme temperatures. Temperature decreases from 2,000 K at observable levels to 1,700 K deeper. Envelope. Molecular hydrogen transitions to atomic, then metallic hydrogen with depth. Temperature rises from 1,700 K to 8,000 to 12,000 K. Stellar heating maintains elevated temperatures throughout. Strong convection mixes the envelope. Core. Heavy element core, possibly 0 to 15 Earth masses, uncertainly large. Temperature perhaps 15,000 to 25,000 K. Core mass affects inflation. Smaller cores allow more inflation. WASP-119b's large size, short period, and bright host star make it an excellent target for atmospheric characterization. We've observed WASP-119b using ground-based telescopes and Hubble Space Telescope to obtain transmission spectra. The large atmospheric scale height, about 700 kilometers, combined with frequent transits every 1.17 days, allows us to accumulate high-quality data efficiently. We can observe multiple transits in a single observing season, improving signal-to-noise significantly. Observations have detected or inferred multiple atmospheric constituents operating under extreme conditions. WASP-119b's atmosphere shows the characteristic signature of ultra-hot Jupiters, atomic species dominating over molecules, water vapor somehow persisting despite extreme conditions, and evidence for high-altitude aerosols. The extreme irradiation creates a chemically simplified atmosphere where most complex molecules are broken down, leaving mainly atoms and a few stable molecules like water and carbon monoxide. While transmission spectroscopy probes atmospheric composition, eclipse observations reveal the planet's thermal structure and heat distribution. The dayside temperature of 2,100 to 2,200 K confirms WASP-119b is among the hottest planets observed. The substantial day-night temperature contrast of 700 to 1,000 K tells us that despite supersonic winds, heat redistribution is imperfect. The planet's rapid rotation, completing an orbit every 28 hours, and extreme heating create a situation where winds can't fully equilibrate temperatures between the scorching day side and relatively cooler night side. WASP-119b's atmosphere is in violent motion, driven by the extreme temperature contrast between its permanent day and night sides. Our circulation models for WASP-119b predict dominant eastward equatorial jet streams reaching 6 to 8 kilometers per second, roughly Mach 20 in the planet's atmosphere, well into supersonic regime. These are among the fastest winds predicted for any exoplanet. The winds are driven by the enormous day-night temperature gradient, 2,200 K on the day side, 1,300 K on the night side creates powerful pressure gradients that accelerate winds to extreme velocities. These supersonic winds have multiple effects. They transport heat, reducing but not eliminating the day-night temperature contrast. They transport chemical species, creating disequilibrium chemistry as atoms and molecules are carried between regions before they can reach chemical equilibrium. And they create intense turbulence and waves that may contribute to inflation through kinetic energy dissipation. WASP-119b's extreme temperatures create a vertically stratified atmosphere with chemistry varying dramatically with altitude. WASP-119b presents two radically different hemispheres separated by narrow terminator zones. The day-night asymmetry on WASP-119b is among the most extreme in nature. On the day side, you'd see a surface glowing white-hot from its own thermal emission, the nearby star dominating the entire sky. On the night side, relative darkness, though darkness at 1,300 K still means glowing dull red like a hot coal. The terminators are where things get really interesting. Fierce winds, rapid chemistry changes, possible exotic weather patterns we can barely imagine. With such extreme irradiation and relatively low gravity, 0.58 g, WASP-119b should be experiencing significant atmospheric escape. Ultra-hot Jupiters like WASP-119b are losing mass through atmospheric escape, but they're so massive that even losing billions of kilograms per second only slowly erodes the total planetary mass. Over a billion years, the planet might lose a few percent of its envelope, enough to affect its radius and properties, but not enough to strip it down to a rocky core. WASP-119b is actively evaporating, but slowly. WASP-119b represents a snapshot in planetary evolution, a world caught in extreme conditions that are slowly but inexorably changing it. Evolutionary trajectory. Past, likely formed farther from star. Migration brought it to current ultra-short orbit. Initial intense heating may have driven higher escape rates when stellar activity was stronger. Present, ongoing atmospheric escape at 10 superscript 1 kg/s. Continuous stellar heating maintaining inflation. Extreme atmospheric dynamics creating unique chemistry and circulation patterns. Future, millions to billions of years. Continued atmospheric escape will gradually reduce envelope mass. Planet may slowly contract as it loses mass, though inflation from heating continues. Eventually reaches equilibrium between heating, escape, and gravitational contraction. Long-term fate. Unlikely to be completely stripped, too massive. Will remain inflated hot Jupiter, but possibly slightly denser and smaller than present. Star's eventual evolution will change radiation environment dramatically. WASP 119b belongs to the extreme end of the hot Jupiter distribution, the ultra-hot Jupiters with temperatures exceeding 2000 K. WASP 119b is not the most extreme ultra-hot Jupiter, but it sits firmly in this category. Its 2100 K temperature, 1.17-day period, and significant inflation make it an excellent representative of planets in extreme radiation environments. WASP 119b remains a high-priority target for JWST atmospheric studies due to its favorable properties and extreme conditions. Transmission spectroscopy. High-resolution spectroscopy across 0.6 to 12 microns to detect molecules definitively and measure precise abundances. Search for exotic species like TO, VO, metal hydrides. Eclipse spectroscopy. Measure thermal emission from dayside at multiple wavelengths to map temperature structure vertically. Detect molecules in emission rather than absorption. Phase curves. Observe brightness throughout entire orbit to create three-dimensional temperature and chemistry maps. Track hotspot location and atmospheric circulation efficiency. Time series observations. Repeated observations searching for atmospheric variability, weather evolution, cloud formation/dissipation, long-term changes. WASP 119b is ideal for JWST because its large size, short period, and bright host star maximize signal quality. The extreme temperatures create strong spectral features. We expect JWST to detect water, carbon monoxide, possibly exotic high-temperature molecules, and to map the three-dimensional temperature distribution, showing how heat is redistributed by the supersonic winds. This will be one of the most detailed atmospheric studies of any ultra-hot Jupiter. While JWST observes from space, future ground-based facilities will provide unique capabilities. High-resolution spectroscopy. Detect individual molecular lines with Doppler shifts from atmospheric winds. Directly measure 6 to 8 km/s wind velocities predicted by models. Atmospheric velocity mapping. Create 2D maps of wind patterns across the planet's disk during transit. Molecular detections. Confirm exotic species like TO, VO, metal hydrides through high spectral resolution observations. Variability studies. Monitor atmospheric changes on hourly timescales, looking for weather patterns evolving. Every observation of WASP 119b contributes to understanding ultra-hot Jupiters as a class and gas giant atmospheres under extreme conditions. Inflation mechanisms. WASP 119b tests theories about how stellar irradiation causes inflation and what mechanisms transport energy to planetary interiors. Atmospheric chemistry at extremes. Shows what molecules survive at 2,000 plus K, and how chemistry operates under conditions impossible to replicate in laboratories. Atmospheric dynamics. Test circulation models predicting supersonic winds and heat redistribution efficiency under extreme forcing. Atmospheric escape. measures mass loss rates, and tests theories about how hot Jupiters evolve over time. Comparative exoplanetology. Each ultra-hot Jupiter studied adds to our statistical understanding of how planets respond to extreme stellar environments. 830 light-years from Earth, WASP 119b continues its rapid orbit. Every 28 hours, every day, and 4 hours, it completes another circuit. The same hemisphere eternally faces the star, scorched to over 2,000 Kelvin. The other knows perpetual night, still blazing at 1,300 K from retained heat. Imagine, if such a thing were possible, approaching this scorched world. From space, it appears enormous, 40% larger than Jupiter, visibly swollen by heat. The dayside hemisphere glows white-hot, thermal emission so intense the planet is self-luminous. Entering the upper atmosphere, you encounter extreme heat immediately, 1,800 K at the outer edges, climbing to 2,000 K as you descend. The atmosphere is thin here, but what exists is moving at terrific speed. Supersonic winds at 7 kilometers per second, Mach 20, race eastward in powerful jet streams, carrying heat from the scorching day side toward the cooler night side. The chemistry is alien. On the day side, molecules are torn apart by heat. Hydrogen atoms, sodium atoms, potassium atoms float through the blazing air. Deeper, where temperatures moderate slightly, a few hardy molecules survive. Water vapor, carbon monoxide, possibly exotic high-temperature metal oxides. The star dominates the dayside sky. Enormous, filling perhaps 30 to 40 degrees of arc, blazing intensely. Its light is more than illumination. It's a physical force, heating the atmosphere relentlessly, driving winds, evaporating any molecule that can't withstand the inferno. On the night side, relative darkness. Though darkness is misleading when the atmosphere still glows dull red at 1,300 K. The host star never rises here. Winds bring hot gas from the day side, but it cools as it circulates, releasing heat to space. The atmosphere glows from its own thermal emission, a planet lit from within by retained heat. Thousands of kilometers down, pressure mounts, millions of times Earth's atmosphere pressure. Hydrogen transitions from gas to exotic states, atomic, metallic, possibly ionic. Temperature climbs to 10,000 K, 20,000 K. At the center, perhaps a core of heavy elements, compressed and heated to unimaginable conditions. WASP 119b has taught us that planetary atmospheres can endure conditions far more extreme than we once imagined. That molecules can survive temperatures above 2,000 K. That winds can reach supersonic speeds while maintaining coherent circulation patterns. That planets can be inflated to extraordinary sizes by continuous energy input from their stars. It has revealed the limits of what atmospheres can withstand. At what temperature do all molecules dissociate? At what wind speed does circulation break down into chaos? At what escape rate does atmospheric loss overtake replenishment? WASP 119b helps define these boundaries. WASP 119b reminds us that planets exist in states that challenge our understanding. That nature creates conditions we can barely imagine. Atmospheres hotter than star surfaces, winds faster than bullets, pressures crushing beyond description. And that by studying these extremes, we understand the fundamental physics and chemistry that govern all planetary atmospheres, from serene Earth to scorched WASP 119b. This is WASP 119b, the scorched world, an ultra-hot Jupiter with dayside temperatures exceeding 2,000 K, inflated to 1.4 times Jupiter's radius, completing an orbit every 28 hours in one of the most intense stellar radiation environments known. A planet where supersonic winds rage at 7 kilometers per second, where molecules survive in conditions that should destroy them, where the atmosphere glows from its own heat. A reminder that the universe creates conditions at every extreme, that planets can endure stellar radiation thousands of times stronger than Jupiter experiences, that atmospheric physics operates from the gentlest Earth-like breezes to the most violent supersonic storms, and that by studying worlds like WASP, 119b, scorched, extreme, pushed to the limits, we understand the full range of planetary diversity throughout the cosmos. It is ongoing. The planet orbits on, and through this scorched world, we see planetary atmospheres tested to their breaking point, revealing the physics of gas giants under the most extreme conditions nature creates. If you sometimes look up at the night sky and think you're able to find something great, this planet proves that you're absolutely right. Next, let's explore K2-228b, the world found by the crowd. 226 light-years from Earth, in the constellation Taurus, orbits a world that represents something extraordinary in the history of astronomy. K2-288b, a sub-Neptune planet with 1.9 times Earth's radius, orbiting comfortably within the habitable zone of its red dwarf host star. Its equilibrium temperature, approximately 230 Kelvin, cold by human standards, but warm enough that with the right atmospheric greenhouse effect, liquid water could exist. But K2-288b's significance goes beyond its potentially habitable nature. This planet was discovered in 2019 through the Exoplanet Explorers Project, a citizen science initiative where volunteers around the world analyzed K2 data that automated algorithms had missed. Amateur astronomers, students, teachers, retirees, people with no formal training in astronomy, spotted the subtle transit signals and flagged them for professional follow-up. K2-288b is the people's planet discovered by the crowd. K2-288b also orbits in a binary star system, two red dwarf stars separated by 53 AU, both hosting their own planetary systems. This makes K2-288b part of a complex gravitational dance, a world where the sky holds not one sun but two, one close and bright, the other distant but visible. A circumprimary planet in a binary system, discovered by citizens, potentially habitable, and in the size range where we understand the least about atmospheric composition and habitability. This is the story of a discovery that democratized exoplanet science and found a world that might, just might, harbor conditions suitable for life. By 2015, the K2 mission had been observing different fields across the ecliptic for 2 years. Campaign 4 targeted a region in Taurus, monitoring approximately 16,000 stars for planetary transits. The data was publicly released to allow astronomers worldwide to search for planets. K2-288, cataloged as EPIC 210693462, was a magnitude 12.9 binary star system in Taurus. During Campaign 4, K2 accumulated 80 days of continuous photometric data. The automated planet search algorithms, computer programs designed to detect transit signals, processed this data and flagged thousands of potential transit candidates. But some signals were too subtle, too noisy, or occurred at just the wrong alignment for the algorithms to confidently detect them. That's where citizen scientists came in. The Exoplanet Explorers Project, launched on Zooniverse in April 2017, invited volunteers to visually inspect K2 light curves, brightness measurements of stars over time, looking for the characteristic dips that indicate planetary transits. We presented K2 light curves to volunteers and asked them to identify which ones showed potential transit signals. The human eye is remarkably good at pattern recognition, often better than algorithms at spotting subtle or unusual signals in noisy data. Within days of launch, We had thousands of volunteers examining hundreds of thousands of light curves, and they started finding things our automated algorithms had missed. K2-288 was among the targets examined by citizen scientists. Multiple volunteers independently flagged the light curve as showing periodic transit-like dips occurring approximately every 31 days. The signal was subtle, depth less than 0.1%, and occurred at times when K2's pointing was least stable, creating noise that confused automated algorithms. But human pattern recognition saw through the noise. I was a high school student when I participated in Exoplanet Explorers. I didn't have any special training, just the tutorial the project provided. When I looked at K2-288's light curve, I saw these small dips that repeated. They were faint, but they looked like what the tutorial said transits should look like. I marked it as a potential planet candidate. I never imagined it would lead to an actual discovery, let alone a potentially habitable planet. After citizen scientists flagged K2-288, professional astronomers conducted rigorous follow-up analysis to confirm the planet and rule out false positives. We performed detailed vetting of the citizen scientist discovery. We analyzed the K2 data more carefully, searching for any signs the signal might be caused by something other than a planet, eclipsing binaries, background stars, instrumental artifacts. We obtained high-resolution imaging to check for stellar companions that could create false signals. We measured the host star's properties spectroscopically. Everything checked out. The transit signal was real, consistent with a planet about 1.9 Earth radii, orbiting every 31.4 days. The discovery was announced in January 2019 in a paper co-authored by several of the citizen scientists who made the initial discovery. K2-288b became one of the few exoplanets discovered primarily through citizen science, a milestone in the democratization of astronomical research. K2-288 is not a single star, but a binary system. Two red dwarf stars gravitationally bound, orbiting their common center of mass. K2-288 is what we call a wide binary. The two stars are separated by 53 AU, far enough that K2-288b orbiting K2-288 at 0.165 AU is gravitationally stable. The companion star K2-288b has negligible influence on the planet's orbit. However, K2-288b would be visible in K2-288bb's sky as a second sun, much dimmer and smaller than K2-288, appearing perhaps like a very bright star or distant sun. This is a circumprimary planet, orbiting one star of a binary pair, as opposed to a circumbinary planet that orbits both stars. In a binary system, calculating the habitable zone is more complex than for single stars, but K2-288's wide separation simplifies the analysis. K2-288b at 53 AU contributes negligible additional flux to K2-288bb, perhaps 0.001 times the flux from K2-288a, essentially negligible for climate. K2-288bb's position in the habitable zone is nearly ideal. It receives about 1.4 times Earth's solar flux from K2-288, enough to be comfortably warm with the right atmosphere, but not so much that runaway greenhouse is inevitable. The binary companion is so far away it has no significant effect on the planet's climate. For habitability purposes, K2-288bb might as well be orbiting a single star, but with the bonus of having a second sun visible in the sky. K2-288bb is classified as a subneptune based on its size, larger than Earth and the largest rocky planets, but smaller than Neptune, placing it in a poorly understood regime. Without a mass measurement, scientists model 3 possible internal structures for K2-288b. The radius valley statistics suggest that planets at 1.9 Earth radii have about 50 to 50 odds of being on either side, rocky/water-rich versus mini-Neptune. K2-288b's position in the habitable zone might favor scenarios 1 or 2, since prolonged stellar irradiation could have stripped a primordial hydrogen envelope through photoevaporation. But we can't be certain without measuring the mass. That's the critical missing piece. Despite uncertainties, K2-288b shows several characteristics favorable for potential habitability. Optimal habitable zone position. Receives 1.35 times Earth's flux, nearly identical to Earth. Not at hot inner edge or cold outer edge, but comfortably in the middle. Subneptune size. 1.9 Earth radii. Large enough to retain substantial atmosphere over billions of years if rocky or water-rich. Sufficient gravity to maintain geological activity. Mature, relatively quiet M-dwarf. K2-288a is 3 to 8 billion years old, past the intense flaring phase of young M-dwarfs. Lower activity reduces atmospheric erosion risk. Likely tidally locked, but potentially habitable. Tidal locking not necessarily fatal if atmosphere can redistribute heat. Models show planets with greater than 0.1 bar pressure can maintain habitable conditions even when tidally locked. Binary system stability. Wide binary separation means orbit is stable over billions of years. Companion has no destabilizing gravitational influence. Proximity for observations. 226 light-years. Relatively nearby for detailed atmospheric studies with future instruments. It was discovered by citizens. This demonstrates that habitable world searches are accessible to everyone, inspiring broader participation in science. K2-288b checks many habitability boxes. It's in the right place, the right size range, around a suitable star. The big question mark is composition. Is it rocky with a thin atmosphere or a mini-Neptune? If it's rocky or water-rich, it's genuinely one of the most promising, potentially habitable planets we know. If it's a mini-Neptune, it's probably not habitable. The 50 to 50 uncertainty makes it both frustrating and exciting. Despite favorable conditions, K2-288b faces challenges common to planets around M-dwarfs, and critical information remains unknown. Without mass measurement, can't determine if rocky/water-rich or mini-Neptune. Composition fundamentally determines habitability. Almost certainly tidally locked. One side always faces star. Requires atmosphere to redistribute heat. Without atmosphere, extreme temperature contrasts. Even relatively quiet M-dwarfs produce flares. High-energy radiation could erode atmospheres, especially when star was younger. No atmospheric detection yet. Planet might be airless, have thin atmosphere, or thick envelope. Atmosphere determines surface conditions. M-dwarf spectrum peaks in near-infrared. Life would need to adapt to red/infrared-dominated illumination rather than Earth's visible light. Young M-dwarfs are extremely active. K2-288 likely had intense flaring in first billion years, potentially stripping early atmospheres. K2-288 be visible as second sun, very bright star. Might affect climate through reflected light or psychological impact on hypothetical life, though negligible energy contribution. The biggest unknown is composition. If K2-288b is a mini-Neptune, we can stop worrying about habitability. It won't have liquid water or accessible surfaces. If it's rocky or water-rich, then we need to consider all the M-dwarf habitability challenges: tidal locking, stellar activity, atmospheric escape. But these challenges aren't necessarily deal breakers. With the right atmospheric composition and thickness, rocky planets around M dwarfs can be habitable. We just need to find out what K2-288b actually is. For decades, tidal locking was considered fatal to habitability. Modern three-dimensional climate modeling has challenged this assumption. If K2-288b has an atmosphere with surface pressure above about 0.1 bar, 1/10 Earth's pressure, atmospheric circulation can efficiently redistribute heat from the permanent day side to the permanent night side. Computer models show that even tidally locked planets can have globally habitable climates. The day side wouldn't be scorching and the night side wouldn't be frozen. Instead, you'd have warm day side, cool night side, and potentially temperate conditions across much of the planet, including terminator regions. On K2-288b, if it has an atmosphere, K2-288 it would hang motionless in the dayside sky, a dim red sun, smaller than Earth's sun, but providing similar total energy. The day side would experience eternal day. The night side would know only darkness, with K2-288 be visible as a bright star in the sky. At the terminator, the permanent twilight zone, conditions might be most temperate, with eternal sunset or sunrise creating unique environments. The single most important unanswered question about K2-288b is its mass. This measurement would immediately clarify the planet's nature. Here is what mass would tell us. If mass equals 3 to 5 Earth masses, this would mean it's likely a rocky super-Earth confirmed. Density 5 to 6 G/cm superscript 3 similar to Earth. Best habitability case, probably rocky with at most thin atmosphere. If mass equals 5 to 7 Earth masses, this would likely means it's a water world likely. Density 3 to 4 G/cm superscript 3. Potentially habitable global ocean world. If mass equals 7 to 10 Earth masses, this would likely mean it's a mini-Neptune composition. Density 2 to 3 G/cm superscript 3. Unlikely habitable. Thick gas envelope. No surface. Measuring K2-288b's mass requires detecting the tiny wobble the planet induces in its host star's motion, the radial velocity method. Faint host star. K2-288a is magnitude 12.9, relatively faint for high-precision radial velocity spectroscopy. Requires large telescopes and long exposure times. M-dwarf stellar activity. Star spots, flares, and magnetic activity create radial velocity variations that can mimic or obscure planetary signals. Long orbital period. 31.4-day period requires observations spanning months to years to measure full orbit accurately. Small expected signal. Even if K2-288b is 5 Earth masses, the radial velocity semi-amplitude is only 2-3 m/s at the limit of current spectrograph precision. Binary companion. K2-288b's gravitational influence on K2-288a creates long-term radial velocity trends that must be separated from the planetary signal. Measuring K2-288b's mass is challenging but not impossible. We need a long-term radial velocity campaign using instruments like HARPS, HIRES, or newer spectrographs. It would require dozens of observations over 1 to 2 years, careful accounting for stellar activity, and sophisticated analysis to separate the planetary signal from the binary companion's influence. It's feasible, but hasn't been done yet. Someone needs to commit the telescope time. For a planet in the habitable zone, detecting its atmosphere is crucial for assessing habitability. Could JWST observe K2-288b? K2-288b is on the edge of JWST's capabilities for atmospheric characterization. If it's a mini-Neptune with thick atmosphere, JWST could probably detect atmospheric features with enough observations. If it's rocky with thin atmosphere like Earth, detection would be extremely challenging. We might see nothing. But K2-288b's habitable zone position makes it worth trying. If we detect biosignatures in a habitable zone atmosphere, that would be revolutionary. Before investing precious JWST time, astronomers need to know K2-288b's composition. Mass measurement is the critical first step. 1. Radial velocity campaign, highest priority. Dedicated observing program with precision spectrographs to measure mass. Would determine density and composition immediately. 2. Additional transit observations. Refine orbital parameters, search for transit timing variations indicating additional planets. Improve radius measurement precision. 3. High-resolution imaging. Continued monitoring to better characterize binary companion and check for additional stellar companions. 4. Stellar characterization. Better measurements of K2-288a's properties, luminosity, activity, composition, refine habitable zone calculations. If mass measurements reveal K2-288b is a mini-Neptune, atmospheric observations become less urgent. It's probably not habitable. But if the mass confirms it's rocky or water-rich, K2-288b immediately becomes a top priority target for JWST atmospheric observations and biosignature searches. The ultimate goal is direct imaging, separating the planet's light from its stars, obtaining a spectrum directly revealing atmospheric composition and surface properties. At 226 light-years, K2-288b is on the edge of HWO's expected range. Closer planets would be prioritized, but if K2-288b is confirmed rocky and shows interesting atmospheric features with JWST, it might make the HWO target list. K2-288b is more than just another exoplanet. It's a symbol of how astronomy is becoming accessible to everyone. Historically, astronomy was done by professionals with access to expensive telescopes and specialized training. But the data revolution has changed this. Telescopes like Kepler generate far more data than professional astronomers can analyze alone. By making data public and creating user-friendly interfaces like exoplanet explorers, we can harness the pattern recognition abilities of thousands of volunteers. K2-288b proves this works. Citizen scientists found a planet professionals missed. Since K2-288b's discovery, citizen science has continued expanding. Projects like Exoplanet Watch, Planet Hunters, and others have engaged tens of thousands of volunteers in astronomical research. Some discoveries have led to scientific publications where citizen scientists are listed as co-authors, formal recognition of their contributions. K2-288b represents both what we've achieved and what remains to be discovered. More planet discoveries, especially around nearby stars where detailed studies are feasible. 226 light-years from Earth, K2-288b continues its orbit. Every 31.4 days, every month, it completes another circuit around K2-288a. If it's tidally locked, one hemisphere eternally basks under the red dwarf sun, while the other knows only starlight, including the distant companion K2-288b glowing as a bright point in the dark sky. We don't know what K2-288b looks like. We don't know its mass, its density, whether it has an atmosphere, or whether liquid water exists on or within it. It could be a rocky super-Earth with temperate oceans and nitrogen skies. It could be a global water world with hundreds of kilometer-deep oceans beneath thick steam. Or it could be a mini Neptune with no solid surface, just gas transitioning to liquid to supercritical fluid as pressure increases with depth. All are possible. All await discovery. But we know K2-228b is real. We know it orbits in the habitable zone, receiving energy similar to what Earth receives. We know it's roughly twice Earth size, large enough to retain atmosphere, possibly large enough to maintain geological activity. And we know something else. It was discovered by people like you. Not professional astronomers in observatories. Not scientists with PhDs and decades of training. But volunteers, citizens, students, teachers, retirees, people from every background who looked at light curves and spotted patterns. People who contributed to humanity's understanding of the cosmos without leaving their homes. K2-288b is the people's planet. It represents the democratization of astronomy, the idea that the search for other worlds, the quest to understand whether we're alone, belongs to everyone. Anyone can contribute. Anyone can discover. Anyone can be part of the greatest exploration in human history. The next chapter in K2-288b's story awaits. Mass measurements will reveal whether it's rocky, water-rich, or mini Neptune. Atmospheric observations might detect molecules indicating habitability or even biosignatures. Future missions might image it directly, revealing its true nature. But whatever we learn, K2-288b will always represent something special. Proof that the search for habitable worlds, for life beyond Earth, is a collaborative endeavor. That discoveries can come from anywhere. That the cosmos belongs to all of us. This is K2-288b, the People's Planet, a sub-Neptune in the habitable zone of a red dwarf in a binary system, discovered by citizen scientists who saw what computers missed. A world 1.9 times Earth's radius, receiving 1.35 times Earth's solar flux, possibly rocky, possibly with liquid water, possibly habitable. A reminder that the search for habitable worlds is not just for professionals, but for anyone with curiosity and dedication. That discoveries await in data accessible to all, and that the next potentially habitable planet, the next candidate in the search for life beyond Earth, might be found by you. The observations await. The planet orbits on. And the people's discovery continues, inspiring the search for worlds where we might one day find we're not alone. If you made it all the way through this video, thank you so much. It really does mean all the worlds to me. Make sure to like, subscribe, and leave a comment about what exoplanet I should cover in the next video. I'll see you tomorrow, and thank you for watching.